All right, thank you. All right, thank you everybody for joining on day 2 of this technology summit. If you are online and your name's Scott Furman and you're not the real Scott Furman, feel free to please go up to the 3 little dots and then you'll have the option to rename and then rename yourself so we can know who you actually are. That would be wonderful. For the people in the room, let's see, we have exit in the front here, exit over here. There through this door, there are the restrooms, exit outside, and a water fountain. There is some coffee in the back. Please feel free to help yourselves as needed. This presentation it's kind of like rapid fire. Each presenter has a max of 25 minutes, so that includes any technical difficulties and questions. I will cut you off at 25 minutes. So if you don't leave time for questions, please stay on and just monitor the chat. For the people here in the room, between Scott, Evan, and I, we will give you a computer so you can type it in the chat and the responder can respond back to you. Also, other lessons learned. Oh, if we do have time for questions and you're in this room, just turn on your mic and make sure the little rim is green, and then you can talk and ask your question, or I can kind of like run it up to you. Just a reminder for those who are submitting proposals, they are due August 9th. Did I get that right? You're emailing them to me? Yes, I got August 9th. I did say it right this time. As we all know, I'm not good at telling time apparently, or saying left from right. So we do what's written in the sheet and where I point, not what I say. Okay, if there is nothing else, but we greatly appreciate all of the presenters, all of your time and coming in, everyone who's coming in to listen. This is recorded and it will be posted on PWD's site once we kind of get everything up and going, so it won't be immediate, but we will get it out there. And we appreciate it. And we'll start in a few minutes once I get John up and running. John, do you have the clicker?
Yep.
Oh.
So you know if you're in the room, the microphone power button is on.
Oh, thank you. Yeah.
Cool.
Yeah, hold it down.
All right, you want me to go ahead and start? Are you waiting for?
Yeah.
One second, Monica. I'll get us going.
Still, yeah.
Yeah.
Yeah, you tell me when it's time.
We're trying to. Oh. Yeah, we're trying to just switch things and then also keep us on schedule. All right, so if you want to go in, so we are starting up with Sea Green first.
So quickly, good morning. This is John Ellersick. I'm president of Next Rung Technology. We're the U.S. commercialization partner of Sea Green. Monica is the head of sales for Sea Green, who is commercializing the OxyPower HTC technology, and she will go first. Go ahead, Monica. Good morning or good afternoon.
Good morning, everyone. Thank you for inviting us to this technology summit. As John said, together we would like to present an innovative solution for the circular, sustainable sludge management of tomorrow. Next slide, please. In very short, we make wet waste valuable. Next. Why is this so important? Well, our civilization produces vast amounts of sludge, nearly 7 billion tons per year. Sludge or wet waste is generated in municipal and industrial sewage water treatment, in pulp and paper production, in agriculture, and in the form of manure. Next. The current ways of sludge handling are simply not good enough. They all come with severe impacts. They cause immense emissions of greenhouse gases. They risk harmful substances leaking out in nature. They're not infinite, or they consume huge amounts of energy. So clearly, we need to find something better. Next. At Seagreen, we want to change the mindset from seeing sludge as a waste stream to seeing it as a source for useful resources. We want to make it valuable. We enable the recovery of carbon and phosphorus, while at the same time ensuring that harmful substances are contained or destroyed. How do we do this? By combining the two processes of hydrothermal carbonization and wet oxidation, we transform the sludge into hydrochar in an energy-efficient way. 5 kilograms of wet waste are transformed into 1 kilogram of dry hydrochar. This means a huge volume reduction of the material that needs to be handled. The decomposition that is emitting methane and nitrous oxides is effectively stopped. The hydrochar is stable, odorless, hygienized, and safe. We go from a substance with negative impacts, high risks, and global costs to a useful product that can find several new applications. Hydrochar has a much higher low heating value than sludge and can be directly incinerated and used as a biofuel. Hydrochar contains carbon and other nutrients and, depending on the origin of the sludge, can be used as a soil amendment product. Hydrochar is a relatively lasting, stable product, and if hidden away, can also present a partial biocarbon capture and storage solution. Next. So what exactly are we delivering? We deliver a process where the water in the sludge is used as process media to dry the sludge. The incoming stream of dewatered sludge or digestate is diluted to pumpable flow and heated up to 200 degrees. The sludge resides in the HTC reactor for approximately 1 hour, long enough to make the hydrothermal carbonization reaction happen. The cellular structures in the sludge are broken, and the carbonized particle will settle at the bottom of the reactor. After the reactor, the thick slurry stream is filtered to produce a hydrochar cake at around 60 to 65% dryness. By adding oxygen, the liquid phase is subjected to wet oxidation and will burn the dissolved carbon in the stream. The COD load in the reject water is thereby reduced, and the exothermal reaction produces the heat needed for the HTC process. Nitrogen is converted into the form of ammonium, which makes it available for optional nitrogen stripping. The unique and patented technology provides an efficient way of converting wet sludge into dry hydrochar. The combination of hydrothermal carbonization with wet oxidation makes the process close to self-sustainable on heat. The energy required to power the process is only the electricity to power the pumps and the compressor for oxygen production. Next, please. So Seagreen is designing its process in 3 different sizes to meet the market demands. The small HTC pilot plant, T1, can treat up to 1,000 wet tons of sludge per year and is aimed at small remote wastewater treatment plants looking for volume reduction and sanitation of their sludge. It can also serve as a first step for validation of the technology prior to decision for investing in an industrial scale plant. The T5 can treat 3,000 to 5,000 wet tons of sludge per year and is designed to meet the needs of small municipalities, treating the sewage from 30,000 to 70,000 people. It can also be combined with biogas and serve medium-sized farms. The T25 is the full-scale industrial plant. This one can treat up to 20 to 25,000 wet tons per year. The plant is built in skids in a modular design, which allows for scaling upwards by adding multiple parallel processing lines. Next slide, please. So who is Seagreen? Seagreen is a Swedish clean tech company founded in 2015. Our headquarters are in Stockholm, Sweden, where we also operate a state-of-the-art laboratory. We have one full-scale plant in operation in Finland, and we have a sales office in Rotterdam. Our mission is to become the global leader in sustainable wet waste disposal and recycling to boost the climate neutral and circular society. In 2022, Seagreen entered in collaboration with Nextrung Technologies to pursue the opportunities on the American markets. Next slide. So our first full-scale demonstration plant is set up at the fluting mill in Heinola by Stora Enso in Finland. Stora Enso is a top-tier global pulp and paper company. The Seagreen plant has been in continuous operation for around 2 years, producing hydrochar from the plant's biosludge. The project shows a perfect site integration where the hydrochar is used as biofuel, replacing fossil peat, and the reject water is fed to the plant's sewer, contributing with heat and nitrogen. Together with the municipality of Heinola, Stora Enso and Seagreen have carried out 2 trials with municipal sewage sludge. These trials have been successful and have produced a high-quality hydrochar at dry solid contents up to 70%. More trials are also planned with interested stakeholders such as Finnish Gasum and with the feedstock from other mills within Stora Enso. Next slide. And currently, Seagreen, together with waste handler Ragn-Sells, the leading waste management company and one of the biggest sludge handlers in Sweden, is in the process of building the second full-scale demonstration and development plant. Here, sewage sludge from the nearby municipal wastewater treatment plant will be treated. The project will demonstrate a full circular solution for sludge that does not meet the quality requirements for direct spreading on farmland. Nitrogen recovery through stripping will be installed as an optional technology, producing ammonium sulfate liquid for the fertilizer market. The hydrochar will be incinerated and the phosphorus recovered from the ashes with the ash-to-phos technology by Ragn-Sells' daughter company Easy Mining. We are also conducting a number of pre-studies with customers in Europe. So RAIM, the leading industrial cleaning and logistics and waste management company in the Netherlands, part of global giant Remondis, are demonstrating a positive business case for the treatment of biosludge from industrial wastewater treatment plants in the Rotterdam area. Treating sludge with HTC and wet oxidation on their site will reduce transportation, increase the flexibility in the offset of the products, and improve the bottom line of the operations for RAIM. With Waternet, the municipal wastewater treatment company for Amsterdam greater area, that is treating the sewage of 1.5 million inhabitants at their plant at Waternet West, Seagreen has engaged in a pre-study to evaluate the Oxypower HTC technology as an amendment to their current sludge handling and anaerobic digestion. This will be evaluated for when the plant is going to be extended to meet the increase in capacity needs. And in France, Seagreen is negotiating a first contract for a T1 pilot plant. The customer is a global giant in the wastewater treatment industry that is looking to evaluate Seagreen's technology in the pursuit of more circular sludge treatment technologies. The plant will be implemented at one of their sites that they operate and will treat a small stream of the sludge. The pilot plant will enable them to get accustomed with the process, the technology, and the outgoing streams, such as hydrochar and reject water. So there is a lot happening in the market of finding circular applications for sludge management. And we are very pleased that in Nextrung, we have found a partner to look at the American market together. So over to you, John.
So just a quick word about Nextrung Technology. We're an engineering consulting company located in Somerville, Massachusetts, out of Greentown Labs, which is America's largest clean tech incubator. Many water and wastewater technologies have come out of there from commercialization, as well as energy, renewable resources, and plastics and fuels. Our mission is to support environmental technologies like this. And since 2017, we've scaled up over 100 clients' technologies to true commercial scale. We work for first of a kind, second of a kind installations, as well as larger scale projects. And our projects range from $300,000 skids up to $200 to $400 million plants and projects. We have been partnering with Seagreen since 2020, when we did their first market study for coming to the United States. We looked at all the available sludge sources in the US and identified municipal biosolids as a key market for them and a good application. I had the opportunity to go to the Hinela mill at Stora Enso, see the system in operation. You can see its size, it's modular. It's about 8 to 10 container sized modules, processing all the solid waste from that mill's anaerobic digester, and literally producing one dumpster's worth of solids a day. Got to see the tremendous sludge reduction in action. We have numerous EPC partners in the United States we work with to do sort of 3D modular design. We would look to fabricate this at one of the larger modular shops in the United States, fully American components and customized for the market. As noted, there's a range of size models. The application we're talking about today sort of matches 2 or 3 of that largest size like you're seeing in this picture. But we recognize there's also smaller, maybe more remote locations that could benefit from volume reduction. In particular, we think this becomes interesting and important when you're thinking about PFAS. The conditions of the HTC do not cause PFAS destruction, that you require much higher energetic level. So primarily you would get aggregation of PFAS in any of the biosolids to the hydrochar itself. So there's also some in the returning effluent, which would go back to the headwaters of any plant it was located at. We think the solution here is to achieve volume reduction and upgrading of the solids at the right locations, collect those biosolids, and then if they do require disposal or destruction of the PFAS, to do that centrally, regionally at one location, as opposed to putting a lot of solutions out to discrete POTWs. The controls right now and the technologies are emerging for PFAS destruction. I think they're complex and costly and really are better centrally located, which is fairly consistent with the plan that you guys are heading towards. So we're ready to deliver into the US market. We have a couple of partners for shops, engineering and design, and operations. As Monica said, the issues in the United States are similar to those in Europe. Places to dispose of biosolids are becoming more costly, or it's being banned completely. People are recognizing that there's greenhouse gases coming out of their municipalities at the back end, and there's something they need to do about it. And generally speaking, if you can reduce the problem to 20% of its original size, you can definitely address costs, even if you have to do disposal methods that are probably eventually going to be phased out. So that's our presentation. We'd be happy to welcome any questions.
Great. Are there any questions in the audience, or if anyone online has a question, feel free to unmute yourself or type it in the chat.
Thank you.
Hi guys, sorry, just a real quick one. With the current legislation in Europe around the STP sludge not being allowed to be used for certain fertilizers and the qualifications, is there something that you see within your tech that might be able to get round some of these things to actually aid qualification of STP sludge so it can be used as a biosolid for fertilizer?
Monica, I'm looking at you for that one.
Sorry. Yeah, I was trying to unmute myself. Okay, now you can hear me?
Absolutely. Thank you, Monica.
Yeah, we obviously anything that is derived from a waste stream is still classified a waste stream, but we have initiated some effort to classify both our process and including the incoming streams and the outgoing products as an end of waste to gain the end of waste status, which would be the first step in achieving product status for example the nitrogen that is stripped out or the phosphorus that is recovered, but also for the hydrochar itself. So we are considering to do this at European level for Europe, and unfortunately I cannot really respond to how that would correspond to the equivalent kind of status change in the US. In Europe, Italy is the first country where hydrochar has been classified as an end of waste product, but only for certain applications. We were working with this European body to do that.
Perfect. Thank you.
Go ahead.
It's obviously very relevant because only once you're able to trade and find applications for the hydrochar, there will be a market value to it. Otherwise, it will still be associated with some sort of disposal cost or limited to the use within your own premise, such as Stora Enso is doing. Yeah,
absolutely. It's a very, very tough one to get qualified, and you're doing the right thing going through the end of waste case basis. It's a long process, but if you put in the hard work to get there, then you're way ahead of everybody else.
Right.
Thanks, guys.
What kind of mechanical dewatering is integral with the Sea Green technology?
So right there, which basic filter press. So it can be blown dry and drip dry, and they achieved like that 60 to 65% moisture content on the paper mill sludge and up to 70% on municipal sludges. So it comes, I'm stationed up in Bryant Pond Station this week. I forgot to bring up my hydrochar samples. But you get a pretty dry product really out of it with a positive heating value.
Yeah. Can you hear me? Yeah. So the reason we are here is because of PFAS and sludge, resulting in the ban of land applicability of biosolids, which is post-processed sludge. Have you all done any work specifically to look for PFAS in the solids, what you call biochar, any liquids or oils that you may produce from your HTC process or your wet air oxidation, and also emissions?
So early study work has been done primarily at universities in Europe. The biosolids samples that have been done there are lower in PFAS also. Okay, so what we primarily saw was not breakdown or destruction of the PFAS at these conditions, and generally a trend towards accruing to the biosolids, which makes sense. It's a very carbonaceous type material, not quite activated carbon, but some of those properties. There was some that did also accrue to a liquid effluent stream, that would be above discharge levels. And so that would be routed back to the headworks of the facility. The possibility of, doing some form of liquid phase capture on that, but generally speaking, that effluent would anyways go back to the headworks of something like a POTW.
Thank you.
Awesome. We had in the chat, what applications in Italy are end of waste?
It's a lot of EU-based questions going on here. Do you want to hit that? Yeah, go ahead, quickly.
I'm actually not quite sure what was the application. I can look that up and send the response to you, Tracy.
Yeah, if you send
I don't
me,
have it in front of me. Yeah.
I can get it to the person who asked. Thank you.
Yep.
All right. Do we have any more questions in the audience or online?
The last comment I'd make about the PFAS is really, we have a nice lab in Stockholm. We're setting up US equivalent We really need to do sampling of representative sludges, and we do have the opportunity to adjust conditions, which we feel will potentially adjust how it partitions, but we primarily solid, some liquid effluent. I was threatened I must stay on time, which we have done.
And you are, and you did a great job. Thank you so much, Sea Green and Next Rung, for coming in and presenting about your technologies. We appreciate it.
Thank you.
All right, we're gonna go on to our next presentation. You want me to or you want her now? Oh, okay, yeah. All right, just give us a few minutes as we start up. You're showing this, you're showing that. Yeah, we forgot to. Go ahead. All right. Are we all set for our next one?
I think so. I'm going to need to get,
And if you are actively not presenting or have a question, please make sure you mute yourself. And if you are listed as Scott Furman and not the real Scott Furman, you can double click the 3 dots and you'll see something that says rename. If you click on the 3 dots, when you hover over the name, that's not you. Go to the next Scott Furman till you see where it says where you can rename it. Are you all set?
all set.
Okay, well, we'll get it over to Hartland.
Thank you very much, Tracy. I appreciate it. And thanks everybody for being here this morning and everybody online for joining. I'm Jim Henderson. I am the Director of Business Development for Heartland's Gasification Technology. And for the record, let's clear this out of the way. We are not a metal band, although Helios want to be a great name, you know. But no, we're actually a serious group of very serious engineers and others that provide technology for water and waste and hard to treat streams. So the technology working here. Yep. So we were, our company was established in 2008, and we are actually officially headquartered in Hudson, Massachusetts. But we have a new technical center that I'm going to be telling you an awful lot more about in this conversation, and that's based in Murfreesboro, Tennessee. So a little more information about that here at the end, and that's really kind of becoming where we're sort of coalescing around as probably a corporate center. But again, we have three businesses at Heartland. The first really is in the oil and gas space, where we are focusing on produced water, a very challenging task. And I think that Heartland is known more and most for its foundational leachate management technology for landfills. And we've been very, very successful when we have installations from Alaska to Florida in that space as well. And we have award-winning projects that we'd love to talk to you more about if time ever allows for that. So I'm here representing the waste conversion business, and which is a focus today on biosolids. And I'm also joined by Brandon Davis, who is our Director of Engineering. And Brandon, I hope you're able there. I see you sharing your video, so that's great. We've got Brandon Davis, who will be working with me this morning to take you through our technology. But on the left, you see our Heartland concentrator. Today, we'll be focusing more on our Heliostorm gasification technology there, which is an ultra high temperature ionic gasification platform that we're launching this year, and to provide specifically assured PFAS destruction. So again, as has been said, on Tuesday, and has been pointed out this morning correctly, we're here to focus on regulatory compliance that has become acutely necessary as a result of recent legislative and regulatory activities in the state. We believe we can provide assured PFAS destruction by virtue of our Heliostorm technology, and we do that by delivering complete molecular dissociation of the feedstock as it cascades and passes through the system from top to bottom. We'll talk more about that in just a moment. But from that, we think then we open up pathways to disposal certainty, right? Because we're producing products that are now innocuous, a char and a syngas, and they're PFAS free, and it now opens up disposal channels that might be more elusive to traditional strategies that focus on, Class B, Class A biosolids. And from that, we're going to operate it as a service. We offer this as a service. We're not here offering a capital piece of equipment for sale. It's a service that we provide. And by virtue of that, we can provide cost certainty for many, many years to come. I mean, we are certainly interested in the long-term contractual arrangements that have been described in the RFI. 10 years, 20 years is certainly within our wheelhouse, and is certainly our interest. Our systems will be operated by certified Heartland personnel to ensure, the performance and the results that are expected, and to, allow us to offer that long-term cost certainty. The risk transfers from the generator to Heartland for those, for those operations, and it alleviates needs around hiring, retention, staffing, training, and all the other things that go along with a new technology. And finally, we arrive back at sustainability, which I know is a key interest for Portland as well as others in the state, right? And we're focused on taking trucks off the road and driving savings not only on the monetary side, but also sustainability capture, around carbon, reducing the carbon footprint. So how do we do it? Excuse me, I'll go out of sync here. Our destruction range operates around 3,000 to 10,000 degrees Celsius, and that is a truthful statement. We operate far and away beyond the temperature ranges of traditional gasification or pyrolysis or incineration. And we're going to describe to you how we get there, but we do this as an electrically driven system. The reactor runs on 480 volt electricity that we're going to generate as a part of the project, as you'll see. The system is scalable. So it's a small footprint. This unit is roughly the size of a refrigerator essentially. But what we do is we match to the generator's capacity by, coupling unit to unit to unit to unit and run them in parallel. And we feed them with a dryer. It's versatile in that it can accept a range of feedstocks, right? So today we're talking about biosolids. We could easily talk to you about methane. We could talk to you about lots of other things, homogeneous wastes, and generate a number of different products as a result of the operational conditions. And we'll talk about that. But today we're going to talk about feeding biosolids and transforming the biosolids to a char into a tar-free syngas. So with that, I'd like to introduce now Brandon Davis, our Director of Engineering. As I mentioned, he's going to walk you through the next few slides, and I'll advance them for you, Brandon, if you'd like to walk us through the details on the unit.
All right, good morning. I'm assuming you can hear me?
Yes. Yes.
All right. Good. Hold on, I'm getting some echo. See if that's better. Still hear me?
Yes.
All right. So the heliostorm is a ultra high temperature plasma gasifier. We call it an ionic gasifier because essentially what happens is we generate free burning electrical arcs. And these arcs, as Jim mentioned, heat the interior of the gasifier up to in that 3,000 to 10,000 degrees Celsius range. And that tends to generate a lot of ions. And that ion field and that ion electric activity then tends to completely dissociate the feed material down to its constituent atoms. As you can see on the graphic to the right, the model that we'd be using for this application is called an M3. And essentially what that means is that we have 3 of these plasma arc modules. And in each of those modules, we have 2 to 4 pairs of electrodes that generate these high temperature electrical arcs. And so you end up with a sort of a cascade of energy, whereas the feedstock falls in, it gets very rapidly heated up and volatilized. And then those volatiles are exposed directly to those electrical arcs and those ions that are being generated. And that tends to dissociate things, and that completely breaks down whatever is in there to their atoms. And that is why, this gasifier is very good at getting very high conversion rates, and also is very good at chemicals of concern like PFAS and breaking them down and completely demineralizing them to the constituent atoms. And you want to go to the next slide, Jim? So our plasma gasifier is a little bit different than your typical plasma gasifier. If you look at the top picture on the right, you'll see sort of a conventional plasma torch used in normal plasma gasifiers. And that has a body where the cathode and anode are contained within the body. The electrical arc is passed between them, and there's a carrier gas that comes through that body, is exposed to that electrical arc, gets heated up and ionized, and then comes out as a plasma jet into the reactor that you're using. The heliostorm is different in that the anode and cathode are separated across the body of the gasifier itself, so that high energy electrical arc is in the gasifier itself. And so that means the feed material is directly exposed to that high temperature arc. And that's sort of the difference, sort of the secret sauce and what makes this gasifier more effective and more energy efficient than your normal plasma gasifiers. So next slide, please. All right, and so you can sort of see here into the gasifier on the picture at the top right. That is a recent picture of our testing here of a demonstration unit looking down into the gasifier itself. And so you can see each of those individual arcs, and you can sort of see the 3 concentric rings as you go down through there, showing the different levels in the 3 modules. And then that very, very bright glob you see in the middle. There we go. You can see the video. So you can see on the left, the very high energy plasma field that's generated in the middle. And one thing to note here is this is looking through the darkest piece of welding glass that you can buy. And even then it's oversaturating the camera's detector. So it's very, very high energy, very, very bright. On the right is another view of it. And you can see as the pellets fall into the gasifier, you can see how they're being rapidly devolatilized. You can actually see the wisp of smoke as things are coming off and being volatilized and generating that gas. And then you can also see the very turbulent nature of the gasifier, that as these plasmas are being generated, that there's a lot of high mixing, a lot of turbulence in there, which is really exposing all the gas and all the feed material to these high energy arcs, exposing them to the ions, rapidly breaking them down. And so it operates very efficiently, typically at about 4 or 5 tons per day for the M3 gasifier. And this is sort of a comparison of where our gasifier operates compared to some others. In particular, we're looking at PFAS destruction here, but this sort of also applies to, the feedstocks themselves and other things that you want to convert. So, typical gasifiers will operate, depending on the gasifier, anywhere from 1,000 degrees Fahrenheit up to perhaps 2,500 degrees Fahrenheit. Pyrolysis operates a little bit lower since you're having to provide the heat externally and you don't have oxygen in there to raise that. And, and also incineration generally operates in that more, maybe up to 1,600 or 1,800 degree Fahrenheit. You start getting demineralization of the PFAS. Some compounds start decomposing as low as 400 or 500 degrees Celsius, but it takes up to temperatures much higher than that to decompose some of the more stable PFAS compounds. But you can see the heliostorm operating up there at 3,000 to 10,000 degrees Celsius is operating at a much higher temperature than these other systems, and also well above the temperatures that you need for that rapid decomposition of the PFAS compounds. And so you completely vaporize everything, turn it to carbon, and then as you fall out of those plasma modules, you have a rapid quench as it cools off, and you reform the compounds basically according to thermodynamic stability. And so you make a lot of simple compounds, hydrogen, carbon monoxide, nitrogen. And what it prevents you from doing is, because that temperature quenches so quickly, you don't get a lot of the secondary reactions. So you don't repolymerize into tars and oils. You don't have a lot of the byproducts that you typically get in other gasifiers. Even the nitrogen itself in the fuel rapidly becomes back into nitrogen and then quenches, so it doesn't react anymore. And so we have essentially no ammonia and cyanide and those sort of reduced nitrogen compounds that usually lead to NOx problems when you go to burn that syngas with other gasifiers. And I believe this is where you're taking back over, Jim.
Yeah, thank you very much, Brandon. Appreciate it very much. Great description and explanation. So I mentioned earlier on that the versatility of our platform, Heliostorm, can accommodate a wide range of feedstocks, right? It doesn't know the difference between biosolids or heterogeneous waste or methane for that matter. It can accommodate it all. And as a result of the feedstock that you feed it, it can generate different products, right? So in this case, we are intentionally focused on processing and managing municipal biosolids and other sludges, but are certainly involved in some other projects as well around, for example, methane and converting that into hydrogen and other opportunities as well. So our real focus as a company right now, again, I'll just emphasize, is on the municipal biosolids, creating the syngas and char. So here's sort of a notional layout of a project, right? So in this case, we're using an example of 50 tons per day of dewatered biosolids at about 20% cake dryness, right? We as described in other systems as well as ours, we begin with the drying step. So we take dewatered biosolids, pass it through a dryer. Any conventional dryer is acceptable. We certainly get great reduction in volume, about 78% reduction there, down to 11 tons of material. And then, as I mentioned and described to begin with, right, we couple multiple heliostorms with one another in order to accommodate the capacity needed for the particular generator, right? So in this case, a single heliostorm unit can manage up to 4 dry tons per day. In this case, we would use 3 with some to accommodate the actual material, plus some built-in redundancy. That leaves us with nominally about 2 tons of of char, which has a wide range of outlets. But what I want to point out is that we are taking through the heliostorm, we're generating our own energy, right? So we're taking the syngas, which is a very high quality and tar free, and we bring it into a gen set to generate the electricity that we need. In this case, about 600 kilowatts. We bring that right back to the bank of heliostorm units, right? And then we have some heat generated from the gen set, and we pass that back to the dryer. And all in, that heat is sufficient generally to satisfy the needs of the dryer and the electricity to satisfy the heliostorm unit, right? So that's a very basic layout and design. There's certainly some ancillary equipment, some balance of plant things to be discussed in that, but that is in its simplest form, kind of the layout. And with that, Scott, Tracy, I'd just point out we can achieve some carbon offsets with doing that. That's why we believe there's a real advantage here to this technology, and that we take a lot of trucks off the road. It was mentioned on Tuesday, and I'll repeat it here. We take 4 out of 5 trucks off the road if we rely on this process, and there's some real gains to be had there. So certainly a question I'm sure in everybody's mind is, documentation around, the assured PFAS destruction piece. And we are undertaking a very prescriptive approach to that. This year, we have 3 events that we are scheduled to do just that. The first one was earlier this year with our M1 unit. And we have, 2 more, but the first one was extremely encouraging. And we in fact, overdosed the feedstock purposely to quantify the amount of removal that we are getting, right? And even with that, we exceeded our expectations, and we now move into testing around the M3 to be completed this year. Brandon, would you like to comment any further on that?
No, you've got it right. I mean, we've done some preliminary testing on the M1 earlier this year. We're planning to do additional testing. As you mentioned, the early testing, we spiked it with AFFF to get a very high amount of PFAS in there, and the results were very, very good. And we're looking forward to the testing we're going to do the rest of the year.
What's good?
Excuse me?
What's good?
What is good in terms of results? Well, we were in the very high 90% range of removal and destruction with a single M1 unit. And we were purposely trying, we wanted to overdose the feedstock so we could actually get a quantifiable measurement and have some residual left in the residual at the end for that first tranche. So it was intentional to do that. We understand that, it's a new technology for a number of folks in the space, and understanding that Heartland has invested millions of dollars of our own money to develop something we're very proud of, and that is our technical center located in Murfreesboro, Tennessee, just south of Nashville. And there we have constructed a commercial scale gasifier, which has recently been commissioned and is operating as we speak today. The purpose of that is to provide client feedstock evaluations, which we're undertaking currently. It serves as an R&D platform as well. But it allows us to take client material, bring it through, perform any level of testing that we determine is appropriate through the protocol that we design through discussions and consultations ahead of time. It's a way to meet our team. It's a way to witness the heliostorm in operation firsthand, and see it for oneself. So we're very proud of that. It is operating as we speak today, as I said, and our official grand opening is in September, where we'll be hosting an event for that. But just a kind of little peek back behind the curtain here, just some quick photos that I actually took when I was there a couple of weeks ago, right? So the team is bringing the system, online, and you can see there in the center, that's sort of the basis of the heliostorm. There's certainly some ancillary things that go along with that, but that gives you a good example, kind of the scale of the unit and what we've been discussing this morning, and some other ancillary balance of plant components there, which you would see if you'd like to join us and see it for yourself. We'd love to welcome you. So our project delivery is really based on a build, own, operate model, right? So we are intentional about owning it and staffing it so that we can deliver the results in a guarantee that you would expect, right? And so we have the in-house team to design it. We have the resources to build it. We can do that without expectation of any client capital up front. We will fully fund the system and we will staff it with our own certified personnel and provide it on a turnkey basis, right? And that's all delivered for a 1 unit fee on a monthly basis, on a per ton basis. There's some other frequently asked questions that I sometimes get, and I thought I'd just go ahead and put them up here, right? So how long does it take to build the thing? It's 18 months from the notice to proceed. Once you give us notice to proceed, we should be up and running and functional within 18 months. It's commercially ready to go today. We continue to do the testing that we alluded to earlier, but we're confident in that and we're prepared to take on that risk today. It is compatible with any commercial dryer, right? So it doesn't matter which dryer you select. I listened to them all on Tuesday, and there's every one of those would be compatible with our system, right? We have relationships with dryer manufacturers and be glad to provide that all under one umbrella. I would like to point out that there was emphasis on digestion as an option. We actually prefer undigested sludge for our system. There's more energy available. And we can accept an undigested or digested material, but we think for simplicity's sake that undigested sludge has some appeal and some advantages. From a budgetary perspective, Scott, you'd likely see us come in at a rate that's advantaged compared to where you are right now, where others in Maine have become accustomed, unfortunately. A single unit does 4 dry tons a day. And we're currently permitted in Tennessee. So there is a precedent for the system being permitted already. And I hope I got in under time. And thank you. If anybody would like to contact me, my information is there. Thank you very much.
You have a few minutes, like 3 minutes for any questions. So if you're online, please unmute yourself or type in a chat. Anyone here? I will ask, so the PFAS testing that you said you're going to be doing, are you testing for PFAS or are you completing like a fluorine balance?
Let me let Brandon address that.
Yeah, so what we're doing is the original test, we didn't do a fluorine balance. We were looking mainly, sort of a screening test. As Jim alluded to, we run as an M3 commercially, which is 3 plasma modules. The test we did was in the laboratory scale with a single plasma module. And the idea there was we wanted to spike to such a high level that you would have some residual PFAS in the gas so that you wouldn't be depending on detection levels to tell you what your removal efficiencies were. For the upcoming test that we're going to do later this year, we will be looking to expand that and do the fluorine balance as well. So, again, the way the gasifier works, we expect that some of the fluorine will actually just end up as salts in the char that comes out. But we do want to sort of quantify how much fluorine ends up in the gas, what compounds those are. So that's part of the the upcoming test plan.
Perfect. Thank you. All right. If there are no other questions, thank you so much for your time and the presentation. Thank you for joining.
Thank you very much.
All right. And we're going to queue up our next presentation. Yes, and as we are switching, as a reminder, if you are not the real Scott Furman, if you wouldn't mind clicking on the three little blue dots, going to rename, and rename yourself so we know who is here, because we do have the real Scott Furman in the audience. Thank you. All right, Sunny M from 374 Water. Anytime you're ready. Thank you.
Awesome. Thank you. Thanks to PWTD for hosting us. So I appreciate it. I'm going to go quick because I have tons of slides to cover. Just a quick origin story. So we started about a little over 10 years with a grant from the Bill and Melinda Gates Foundation. One of the recipients happened to be Duke University, which is where our founders are from. The idea or the challenge at the time was to reinvent the toilet. So essentially to take municipal sludge and convert that into something benign or useful without using a whole lot of infrastructure or utility. We chose supercritical water oxidation, which I'm going to cover in subsequent slides, as the pathway to get there. And after about 5 years of working and developing this technology, we spun out to form a privately held company called 374 Water, which last year we went public, and we now trade on NASDAQ. We are based in Durham only because that's where Duke University is, but we are fully remote. So we work, we have folks working from Europe and Asia as well. So what is supercritical water oxidation? To get to that, I just always cover the water part first. So water 101. We know of water as solids, liquids, and gases. We know how those phase changes occur. And typically, most folks, if you ask them, they would say it's because you have to change the temperature and you can get from one to the other. Often we don't pay attention to the second most important physical attribute that contributes to phase change. And that has to do with what I'm going to cover next. So if you were on the beach, you can boil water at 100 degrees C. So this is a well-known fact. This is an average though, because there's still some variation in gravity, I would imagine. But if you were, say, in Denver, you would need far less of a heat to get your water to boil. And this has to do with the atmospheric pressure being lower. So with lower pressure, you can boil water faster. On the contrary, if your pressure is high, it takes a lot of heat to boil the water out. So pressure is the second most important factor in phase change. And the reason I bring this up is they counteract each other. And in understanding this concept, we are able to then perform what we are trying to do in the next step, which is go to supercritical, take your sludge and go to supercritical without having to undergo any phase change, intermediate phase change, which typically results in things like what you'll see in your boiler. You'll see some scaling on your boiler. That's because your water evaporates and leaves out the solids. Whereas if you were doing it under pressure, the water will never evaporate. That's exactly what we're trying to do here. So we go straight from sludge to supercritical. Now, how do you get to supercritical? It's actually very simple. This is not a complex process. Most people think it's it's rocket science, but it's not. In this graph, you can see temperature on the x-axis and pressure on the y-axis. And you can see here, depending on where you are on the pressure and temperature, you could be you could have water under solids, liquids, or gas phase. We are treating most of our waste in the water or the slurry phase. So sludges around 15% is typically what we are targeting in the municipal application. but it could be pure AFFF, which is a liquid. So we could be processing liquids as well. So it really depends on the caloric content of the waste as opposed to the dry solids of the material. So how do we get from this waste down to supercritical is first you elevate the pressure. So you go up to 220 bars or so, and then you increase the pressure such that you always stay inside of this phase transition curve. So you'll never cross into gas, you'll go straight from waste into supercritical. Again, this helps prevent other challenges like, say, with thermal hydrolysis. If you heat the sludge up, you will form refractories because your protein gets cooked up. So you will form refractory carbon and nitrogen and phosphorus, which you cannot biologically degrade. So these are products of incomplete processing that you can avoid if you do it right. And that's exactly what we do. So why do we need to be under supercritical conditions for us to oxidize the carbon out of this equation? And again, that has to do with another property of water, which is the solubility. So we know under room temperature, water is a universal solvent and it's able to dissolve salts, but it's not often able to dissolve organic material. When I say organic material, I'm talking about products or compounds that have carbon. For example, if you take a cup of water and if you add salt, the salt will immediately dissolve and dissociate. So you can't see the salt, it'll be clear. I mean, you can't, it's gone. But if you add pepper, the pepper will either float or sink depending on how much you add, right? That's because pepper has carbon in it, and the salt, NaCl, has no carbon in it. So water is a universal solvent under room temperature for ionic bond compounds like salts. It's not very good for organic compounds. There are a few exceptions. That's why I had most here. Exceptions being hydrophilic organics like sugar and alcohol. We should avoid both, I'm told. Why I bring this up is when we go supercritical, that property of water actually flips 180. It goes 180. In other words, the salts will now precipitate out of the water, and the organics, the pepper, will now dissolve, dissociate, and disappear. So pepper literally will go from being grayish black to invisible in the supercritical fluid. So pretty much any organic waste, it could be poop, it could be PFAS, it could be piece of ham, whatever you throw into it, it will completely dissolve, dissociate into its most elemental compounds. Pretty much similar to what Brandon mentioned earlier about dissociation under plasma. The same thing is happening because supercritical is halfway between boiling water and plasma. In fact, it's not halfway. It's kind of like much closer to boiling than plasma, because plasma on the screen would literally be out there. Yeah, so this property of water, the unique property of water to dissolve organics, is what we're trying to tap into. And with that, all we need to do is introduce an oxidant. In this case, we use air as the oxidant. So simply taking a waste, any organic waste, bringing it up to supercritical condition, add air, and your resultant is carbon dioxide. I didn't do that. Clean water, and you get your minerals. So when I say minerals, these are salts which are formed because the inorganic fraction will eventually form a salt, including your fluorine, if you have PFAS in your waste. And it's an exothermic process. It's highly exothermic, in fact. So here in this example, sugar, I'm using glucose as a very simple example. You can see it's producing tons of heat. So when you see this negative number on the enthalpy of reaction, that means it's an exothermic reaction. It's producing the heat. In this case, I'm showing an example of PFOA. Again, with PFOA, we would add a base to go with it. And you can see it's also producing tons of energy. Sludge is around 9,500 kilojoules. So sludge is far more energetic when you oxidize it than any of this compound. So it's a highly energetic process. And you're able to do all of this in a matter of seconds. So in a matter of seconds, you go from organic waste to clean water and energy. How does it work? So it's a pretty simple setup. Our reactor is a piece of pipe. So it's not a very complex machine at all. It's a piece of pipe under pressure. We take ambient air, which is our oxidant. We use a scuba compressor. That's why there's a scuba guy in there, because a scuba tank is at 3000 PSI. We are at 3200 PSI. We take ambient air, preheat it with the heat of reaction, and we do the same thing with the waste, preheat it with the heat of reaction. And simply by combining those two and introducing it to the reactor, you can take it from subcritical, unphase changed gas and water or liquid, and you go supercritical into one homogeneous medium, and that's where the oxidation happens. The nice thing about a process like this is it's all happening under one homogeneous phase. It's not solids, liquids, and gases we are treating supercritical, which means your kinetics needs to be only set for just that one medium. We are not worried about how rapidly the gas is expanding in an incinerator. So we don't have to worry about 3 different kinetics to go after PFAS or any other compounds. We destroyed all under one phase, very simple. The outputs, again, are very simple and benign. You get your carbon dioxide, which we do count, even though it's biogenic carbon dioxide, we would count it as a greenhouse gas. You will produce energy from the expansion of the gas itself being captured in an expander. You will produce distilled water. About 70% of the water, 70% of the water will come out as a distilled water, which means you can either disinfect and discharge, or if you have a potential for reuse, you could use that. And the other 30% will essentially carry those inorganic salts out. And if there's any residual PFAS that will come out in this water, which comes out with the mineral, it's not in the air, it's not in the distilled water, and I will show data. So this is just an example of how it looks. It's not very clear on the screen, but you have waste going in, you get your distilled water, and you also get your minerals come out in an effluent, which needs to then settle out, and then you will separate. There's a separation step that needs to be taken into account for, which we don't in our process right now. So it doesn't matter what you put in, you can get the same output. In other words, if PWD has a drinking water partner who has GAC at their facility and they want to get rid of it because it has PFAS, you can do that too. This is an example of GAC being slurried and processed. Of course, GAC being highly energetic, you'll have to dilute it down. So if you blend it with your sludge, you're able to still process it. So again, we are trying to target a certain caloric content going in, so it's not necessarily the percent dewaterability. Now, I already touched a little bit about how efficient it is, but I'm going to show you some data. This happens to be a sludge which had lime stabilized sludge from your state. And you can see here, we took about 6 seconds to treat this. No co-fuel, we were just dewatering it up to around 16% cake. You can't see the data here very clearly, but I've summarized it here. We found about 24 derivatives, and I'm going to give you a copy of this. And if I'm not already shared this, you can have the entire paper. And we got about 99.9% elimination. Now, I'm sure people will say, why not 100%? We can get 100%, but it's not practical to be using a system to get 100%, because in order to get 100%, you'll have to run longer or run it at a higher temperature, both of which will cost you money. So instead, if you do want to get up to the near 100%, the other way would be to simply club this with a sequestering technology downstream. So you would treat the waste, and only a fraction, about 30% of the liquid from your sludge processing, which again is a fraction of your total wastewater effluent, would then be treated using a GAC or an ion exchange to get down to the levels of discharge water that you need. So if you want to produce drinking water quality from a process, you are able to do this by combining this. Now, when you're spent this GAC or ion exchange or whatever, you can then take that and recycle it back, and we can destroy that as well. So essentially, we are able to destroy no matter what we put into the system. The same can be done in a 2-step process. Again, we don't recommend this for your scenario because we are not, the first scenario would be just as effective. So have we done fluorine balance? Of course, we have done fluorine balance. We started as an academic endeavor, so of course, we studied the hell out of this. We were able to get down to 100% recovery on our fluorine balance. So this is, of course, took a lot of effort. What we found is if you need to get up to that 100%, you really need to be running it at 37 seconds instead of the 6 seconds. which again is not practical because 6 seconds, you can push X amount of volume. At 37 seconds, you're only a fraction of it. So your throughput will suffer if you go longer. You can increase the temperature too, but the ideal scenario is it get about 3 logs or 3.5 logs of PFAS through your process, and then take the small slipstream or slide stream that comes off or the process as an effluent, treat that using an ion exchange or GAC. That combination, I think, is the best way to go about and the most cost-effective way of doing this. Quickly, we did check for emissions as well, because that's a concern. Because when I showed the balance of 99.9%, we took into account the solids fractions, the liquids fraction, as well as the gas fraction. This was a test that EPA did on our process. The gentleman is from EPA. We have done all kinds of tests with the SUMA canister, with solvent tubes. We have also done OTM 45 analysis. And we are also doing another test end of this month, again for EPA for another project. So we have seen that there are no PFAS coming off of the emission, which we're able to guarantee. So I think that's another thing that I need you to pay attention is if somebody says they can do something, you may want to ask them for a guarantee. So how does it compare with others? I'm going to skip this slide for the sake of not being controversial. This one, I think, is most interesting for you all. You can see here incineration, pyrolysis, gasification, higher temperature, lower pressure. Drier again, lower temperature, lower pressure, and it doesn't do much other than just reducing your volume. HTC, wet air oxidation, HTL is getting closer to where we are, but really supercritical in this boundary is all by itself in there. And the reason is that's the only process that works in a homogeneous state. There is no solid, liquid, gas. It's all supercritical. That allows us to be able to really fine tune and be really efficient in getting rid of any kind of recalcitrant waste that you may have. And that's, you are not able to do that with any other technology. Without having any product of incomplete combustion or reaction or a char or an oil or a coal or whatever the case might be, they all end up with some PFAS in it as well. And all thermal treatments are not created equal, because there is thermal desorption of PFAS that can happen at a much lower temperature than you would imagine, even at temperatures in some of the dryers that are being operated in. So you can see here, and again, the source is right here. You can go study this. This study was done on soil. So you can imagine it. Some of the soils that were studied were clay, which has far more propensity to holding on to organic material than sludges are. So you can take this results and somewhat correlate it to the sludge application. So I'll let you look at this in more detail when you get the slides, but essentially what this is showing is even at temperatures as low as 150 degrees C, you are able to volatilize PFAS compounds, which means it's something that we need to worry about. We have to look at it on a holistic solution. We cannot be just looking at it as, hey, there is no PFAS coming in one particular stream. That means PFAS is destroyed. That's not necessarily true. Another thing we need to pay attention is at what detection level those PFAS are being reported, because I've seen reports where someone had 2 parts per billion as the minimum detection limit. Guess what? 2 parts per million, there is no PFAS in your sludge in Maine at all. Ask him. You need to look at parts per trillion. You need to look at really low numbers. Anything that's not less than 1 parts per trillion being reported, those numbers has to be questioned. So which is the right one for you? So we figured the biggest one is the right one for you. So I looked at the regional solution option that you had, the biggest one. But unfortunately, I think I was telling Scott earlier is we'll only be able to provide this in a couple years from now. We can do the smaller one, we can do the medium one, but we are going to get there eventually. We wanted to do it in a step format. We didn't want to go from the smallest unit to the largest unit because we have seen other people try and fail. So we decided we are going to crawl and then walk and then eventually run. So that's exactly how we want to do. Even at the risk of not being able to work in Portland, that's just the step we want to take. We are not going to rush ourselves out of business. So this is your east plant, and I went ahead and already plotted where you want to put your system. And this is what you're going to treat. So this is the regional option, 196 metric tons. I use metric tons. I'm sorry, we can convert it back to regular tons, I guess. We just need one of our AS200 system. It'll produce electricity, it'll produce thermal energy, and it'll produce clean water. So it's going to produce those. It's not going to consume those. So you're net positive on electricity, energy, thermal energy, as well as, of course, your water. You will produce phosphorus-rich minerals. And if you still struggle to dispose it off in a land application, which I foresee could be the case, you will dispose it off along with, say, a couple of weeks worth of sludge, because we will be off for a couple of weeks. You would imagine no system runs 100%. So you will still end up spending maybe $1 million on disposal on an annual basis, but you're offsetting on your energy costs, as well as all the money you're going to save from not going to the landfill on a regular basis with either dried product or char or whatever the other products might be. So I also went ahead and updated the PFDs. You don't need that. You don't need that. You don't need that. You don't even need that. In fact, you can take your sludge and go directly to dewatering, putting it to our system. And then you can take the salts to land use. If not, you can skip the two. So this is how it started, and this is how we are now. So we do have a system that's getting ready to go to Orange County Sanitation. It is all made in the US except the expander. So it's, I would say, 94%, 95% made in the US, right here in Indiana. And our goal is, we do have a lot of projects. So you're not going to be serial number 1. You will probably be 11, 12, 13, 14 maybe. But we can rewrite the headlines. I saw this headlines with another name and I just added mine in the end. That's it. So how can we help you? So we can reduce your cost of sludge management, because you're not going to have sludge when you're all said and done. That's number 1. We can reduce your equipment. You're not going to be needing 4 steps to get there. You just need 1. And we are absolutely able to guarantee you that you won't have any risk on liability, because we know we can destroy PFAS in solids, liquids, and gases, and we can guarantee it. So thank you.
Great, thank you. Does anyone in the audience, we have about 3 minutes for questions, or online? Unmute yourself. Any in the audience?
Hi, Tracy, it's Andre.
Hey, Andre, go ahead and ask your question.
What's the detention time at the 30, or excuse me, what is the volume at that 37-minute mark? What kind of volume's going through there?
37 seconds.
Excuse me, 37 seconds.
What was the flow rate in the unit that we tested?
Yes.
About 1.1 gallons per minute. But remember, that's our smallest unit we have. The biggest unit we will have the one that we are proposing for, or rather the one that we will recommend for Portland, would be around 45 gallons per minute. And again, this gallon per minute may be completely arbitrary and useless, because it has to do with the amount of calories going in. So we are going to be dewatering it to adjust to get to a caloric content of 2.5 megajoules per kilogram. That's 1,100 BTUs per pound for the rest of us.
Understood, thank you.
Thank you.
To follow up on that, when you say it's so if you have, I guess, a lower organic content in the sludge, does that mean you have to feed more to get that caloric value, or you need to add something to up the caloric value?
No, we would dewater it more. So if you have digested sludge, because you've already taken the carbon and reduced it to methane, we would dewater more to say 18% instead of 15% and treat that. So we can just adjust the dewaterability to get to the caloric content that we need.
Okay,
Thank
great.
you.
We have time for one more. Is there any? All right, not hearing anything. Thank you, Sunny.
Thank you.
appreciate the presentation, and we'll go ahead and queue up our next one.
Hey, Tracy, can everybody see that okay?
Yep, yeah, we're seeing it. Do you want to just flip through and make sure it's working? Flip a couple. Perfect. Yep. You are ready to begin whenever you would like.
Beautiful, beautiful. Thanks everybody for the presentation today. Also congratulations to the tech teams that have been on so far, some impressive stuff. So we're Utopia. We're actually a development house that looks at taking technologies into our development projects. And today we'll be presenting 3 techs or technologies that we're going to put together that we feel combine all of the utilization methodologies that Portland requires. So that what you'll see is this is a typical CSTR plants. Just for sake, we don't dam these things, but everything we've been working on is literally to take away all of the inefficiencies that CSTRs and CHP systems have. So in the terms of throughput values for the length of time for retention in solids to gas yields, and then the low efficiency of gas to the CHPs in terms of low efficiency burn rates, and then obviously NOx, SOx, and emissions that come from the burning of the gas itself. So we've looked at the plant of tomorrow, is what we like to call it, the circularity at heart, the full shebang. We take all organic waste streams into our reactors, which I'll show you in just a second, from slaughterhouse waste, organics, industrial, SDP, animal manure, typical biogas, feedstock. And in terms of the byproducts we can create is obviously biogas, LNG, CNG, CO2, clean CO2 as a sellable byproduct out to the market, back for food grade and farmer grade. Clean energy, which you'll see from our solid oxide fuel cell, and biofertilizer. But there is a caveat behind the biofertilizer that it is completely dependent on the feedstock. And in this case, in terms of STP waste, we won't be creating fertilizers. So this is the system that we have. It's Antec. It's a Norwegian-based bioreactor. It's a flow reactor that we have. And this enables us to drive the feedstock through at methodology or speed and control methodology that allows us to look at all the inefficiencies that CSTR brings and get rid of every single one of them. So you can see that now we have a single size of reactor. We used to have 3 sizes, but now we've got a 105 meter cube reactor, and they can be double stacked, and they're all made from fiberglass. So very lightweight, very easy, and very efficient in their nature. And why are they efficient? And it's typically because of the surface area that's inside the reactors themselves. So standard CSTR systems that you'll see down here, which you saw at the very beginning, typically they'll have around about 200 meters squared of bacterial surface area. So what that means is in typical anaerobic digestion, when you have solids into the reactors, the bugs have to connect to those solids to eat the solids and create the gas. So what we've created is a much, much higher surface area bioreactor with around about 1,600 meters squared of surface area for those bugs to attach, and then therefore more surface area for the actual organics to turn into gas. And you'll see obviously a honeycomb structure there. That's not actually what it looks like. It's just a representation of how we kind of showcase how it's done. But we've based this whole thing around a cow's stomach, because cows are obviously the most efficient at producing methane, and they're also the most efficient at managing their organics through their bodies. So we start off with a hydrolysis system that breaks down every part of the media down into a homogenized waste stream, which includes the carbohydrates, fats, and proteins. And then we have an acidification project, so a product or process included within the reactor. So once we have small homogenized waste streams gone through, then the molecules that are, or the growth of the organics that are left The acids break those down into further gas production, which gives us the acetic CO2, hydrogen, and then obviously methane and CO2 production. With the yields that we're looking at, because of the surface area, typically the throughput values that we can get on this, we're looking at around about 3 to 5 days of processing time, instead of a 45 to 60 day that you would have on a standard CSTR system. So much more processing rate at a much smaller footprint. And also the gas yield, typically we'll get an 80% gas yield from the organics, and including with reason of why we don't really go for the biofertilizer is because the anaerobic digestion process so is aggressive in here that we reduce the organics by around about 85%. So the bugs basically eat everything and anything they can that's available within there, other than the non-digestibles, which are typically fibers or any kind of carbon that's left through there. So the entire system is completely remotely operated. If you wanted to, you can put it on your iPad or your phone, and then you can remotely operate it from anywhere in the world. And the scalability is exactly what we've focused on to make sure that we can scale and downscale these processes as much as we want to. So we've been working very diligently to make sure that this whole system is as efficient as possible. Then we come on to the PFAS side of things. So if you can imagine on a standard CSTR system, what we have is, a very thick sludge or digestate that comes out the back end. In terms of the Antec digestate, it's almost like a cup of tea, so you've basically got very little organics in there. It's a very loose, very thin liquid, which is absolutely perfect for the Antec system. Now, what the Antec system does is destroys the PFAS completely on site. And that is through the methodology, as you'll see here. So it's predominantly been tested through landfill leachate, but to be honest with you, with what you get in landfill leachate and the makeup and the entirety of there, it pretty much works exactly the same on a thinned out digestate that we'll find from the back end of our bioreactors. Now, what it does is it breaks down the covalent bonds and the free electrons and breaks it down into a mineralization part. So the radicals that are left behind are broken down into its mineralization and then completely destroyed, so that you basically have 99% PFAS reduction throughout the entire process. So what we can see from here, from the testing that they've done so far, and it's been pretty impressive, is they have a lab scale test line that what we like to put together with our Antec lab scale. And we'll come in and we'll do a full lab testing to get the full spectral analysis of all of the componentries within the actual phases themselves. And then we'll run it through the actual the bioreaction and then a physical chain to go back into the Antec lab scale testing as well. We're currently scaling up to the system that you've seen there, which is the larger scale. Sorry, I'm just going to flip back. So this is the next scale of the system that's about to be deployed. That's currently being manufactured as we speak. So it's completely in line and completely independent from the digestate that comes off the back end of where we're at. And that's exactly what we're trying to do here, is that we're trying to increase modularity so that it matches the same scale of our bioreactors compared to our PFAS destruction systems, so that we can open the door to allowing the actual sludge and the STP sludge to be used as a biogas medium. What we want to do is follow the energy chain right the way across, every single part of the organics that we have. We want to make sure that we can monetize them as far as we possibly can do, and make sure that we take that completely within the EPA limits that are there today. So we think that, and we don't think, we know that putting these two technologies together is going to make a huge difference in terms of opening up the STP sludge for biogas production. And again, because of sizings and limited space in typical STPs in towns, you've got a lot of smell issues. You've got a lot of typical biogas, organic processing side issues. But every single thing that we have is completely closed loop. So there's no odor emissions. There's nothing there that we can deem to be an issue inside small townships. And then in terms of the power generation, we look to the Bloom energy cell. And the reason that we've done that is for two reasons. So the first reason for Bloom is because of its efficiency. So we can polish up the gas to come into the Bloom cell at 90% plus efficiency. So if we looked at the CHP, the combined heat and biosystems of just burning the gas, we're increasing efficiency by quite a considerable sum. And then also the space constraints as well. These are very tight-knit systems that are very, very efficient in space and energy generation. But also the fact that when we're looking at CHP, we have emissions. With a Bloom cell, we have absolutely no emissions whatsoever, other than a hot gas that's coming from the actual electrolyzer itself. So also with some of the issues in terms of transmission lines and being able to actually get the energy on the grid, what Bloom and its always-on system, or what we call it would be a microgrid system, enables to actually smooth the load of renewables that are coming online and the demand of the grid. So if you imagine that within a lot of the renewable sites that are out there, so a lot of solar power that's going to be put on some STP sites if you have space, or wind, these carry variable loads that are very difficult for the grid to understand how to take it because they can't smooth the load to accept it when it needs. So this reduces the actual capacity and effectiveness of renewable energy. If we were to put it through the Bloom cell and through the actual system itself, then what we can do, because we know by the millisecond the gas that we're producing, and then by the millisecond the energy that we're producing, we can actually smooth that load on the grid, because we've got a very stable power generation that we can call off from end to end, either on the draw demand or the production demand, by generating the renewable power through the actual grid line itself. So they have multiple deployments. As you'll know, Bloom is all over the place right now. You're talking Ferrari, Home Depot, Walmart, you name it, these guys are in there. And typically they're there because with the natural gas side, so they're taking natural gas and then actually turning that into power directly on site for private wire contracts. But as you can see as well, they're using sort of a car park methodology as well. So in terms of large STPs, so I'm actually in Muscat, Oman right now, where we have 125,000 cube per day system that's being put into place. It's around about 69 megawatts. So in terms of space constraints in cities, being able to bunker and to be able to car park and stack these systems like we can just reduces the amount of space that we need to be able to deploy these systems on there. And obviously, I was saying before, the combustion rates are extremely positive. 99% reduction on the emissions, 40% more power. The flexibility in terms of what we can take across. We can actually do dual fuel, so we can do electricity, and we can do take the gas and turn it into a trucking fuel or jet fuel if we wanted to with a GTL system. And then obviously the efficiency of the sizing and the lower based on the OPEX. So typically with these systems, we can put it in as a full PPA basis. So no money down. We just put it in and then split the revenue on the back end. And again, because we're a development company, we typically don't sell any of these systems. We put them together. We bring all of the money. We bring all of the training and expertise for the team that will come in to run these things. And the great thing, I guess, towards a sewage treatment plant that's worried about custodianship of the waste, because we will rent the land from the area that it needs to go in. As soon as that waste crosses the line into our unit, then we become the custodian. It becomes our problem. So therefore, we're not going to pass back any problems to the STPs. So we, as developers and technologists and investors, we've got to be extremely confident that we're not going to leave ourselves any problems in the latter, so that we don't start to bust down our IRR or MPVs of our investment portfolios. So in terms of the status quo of against flaring combustion engines, and everything and above, we really are a kind of cut above the rest in terms of the efficiencies that are out there, and the available options to us to actually go and drive efficiency as far as we possibly can do with the cleanest, most efficient environmental targets that we can hit. So many questions. It's a rapid fire fly through, because usually I talk for ever, but we have all of each of the prospective stakeholders from each of the technology companies on the call. So if you want to ask any questions, they'll be happy to answer your questions.
Great, thank you. Yes, you have plenty of time for questions.
Excellent.
So if there's anything online, please unmute yourself. Is there anyone in the audience? I can run the microphone on, or you can turn yours on. Hold on one second. Hold on one second.
The clarity systems, that's dealing with water. PFAS in water, right?
Absolutely. Yes, correct. Yeah.
So you're assuming it all gets out into the water through the.
Yeah, so this is exactly the point of the digestate from the back end of the system, because we know that the majority of the solids from there will be gone. It's really a fibrous, non-digestible that's left in there, and we don't think that the PFAS will be attached to those non-fibers. It's going to be an extremely small percentage, micro percentage of traceability within the actual system itself. But the Clarity team, I don't know if you want to talk to the system in terms of solids being within there and the destruction of PFAS against those solids.
Yeah, from that standpoint of view, again, because there's no physical barrier within the Clarity system whatsoever, the solids content is really negligible. It's more of, if you can pump it, essentially we can treat it at that point in time, because there is no physical barrier between the anodes and the cathodes within the electronic system itself. So again, coming off from a digest standpoint, they're lower solids before you dewater and really thicken it up, then to really go after those PFAS, the PFOA, and those bonds, it really is an issue when it comes to the treatment process itself.
As far as what solids are left in the flow.
Correct. Yeah. Again, we look at where your PFAS may be bound up. The electrochemical oxidation itself doesn't really care. What media that you find those bonds, you run a liquid through your electric field overall, it's going to oxidize, pretty much anything that's in there itself. So, the media is negligible in terms of what we're looking for from a PFAS destruction standpoint. So whether it's in straight, the digestive stream or the digestate or before, it really doesn't matter in this case, because of the Antec system above it, processing for the biosolids and there's a gas downstream of Antec in their digestive stream is perfectly suitable for the technology overall.
Okay, as long as it's thinned down to a liquid, you can deal with it.
Correct. Yeah, and that's where we come out. As long as you can pump it, we can treat it essentially.
Okay, thank you.
Yeah.
I'm just a little confused here. What kind of solids residuals do you get out of the system? What's left besides water?
It's basically, so there's very little. So the screening that goes on the front end in terms of the hydrogenation really destroys everything, in its wake to a very, very fine particle, less than 1 micron. So really all that's left is non-digestibles. So typically something that takes longer to digest than a typical organic. So let's just say that you may have wood chips in there for whatever reason, you know, that it's got through, or sand that's within that side of things. These will drop out into the actual suspension of the bottom of the tank, and will be driven through the actual unit. But the hydrogenation piece really, it takes it down to a very, very small particle. So if you have you know, if you're familiar with the different types of digestion with, you know, with food waste and high rate organics, high calorific organics, this is the system that's absolutely perfect for it, because the bugs will rip into them very, very quickly and off gas. So if during, you know, let's just say we set the flow rate at 4 days or 5 days digestion to allow us, as the plug flow and the drive runs through all of the organics, if it was a fiber, so if it was, you know, if it was a piece of wood, or if it was something like that, typically that would take a very, very, very long time to digest in a digester. So any of the solids really is anything that would be longer to digest than standard organic digestion. So we would classify it as a non-digestible. Eventually it will be digested, but just not in this case.
Yeah, so there have been studies where we've shown that longer chain compounds tend to be hydrophobic, and they tend to jump onto solids in wastewater. So that's why when you look at the fraction of those legacy compounds like PFOA and PFOS, you tend to see more of them in the sludges as opposed to the liquids. The short chains remain in the liquids, which again, you know, in your case, with the cellulosic material that you're not able to digest within your 4 or 5 days, those will then be the center for those PFASs to basically accumulate on, I would imagine. I'm speculating here because I don't know your system.
No, absolutely, yeah. You're correct. Yeah, no, absolutely. And in that case in point, you know, I was a massive fan of pyrolysis, loved it. You know, I thought, you know, pyrolysis was the solution for me, and I'm not knocking pyrolysis at all. But in terms of the Clarity system to destroy the PFAS and the liquid function, or the liquid digestate that we have from the back end of the system, because we've destroyed so many of the organics, it didn't make sense for us to go and put an aeration system and you know, anything to take out the TDS or the TSS and float that off as a sludge stream, and then dewater it and then put it through pyrolysis. So in this case, what we're seeing is that any of the non-digestibles that are there are bunkered for a very long time, because there's a very small amount of them, and screened. And if they are there, then they will be put to pyrolysis on site. So one of the systems that we have in Europe right now, in Norway, is a system called Standard Bio, and it's a selective biochar process. So for the remainder of the solids that are there, they'll be run through a pyrolysis system to make sure that it's zero discharge. We don't want anything leaving the site, so we're happy to take the commercials in terms of the actual capital to make sure that that's zero discharge.
Great. We have time for one quick question, if there's any remaining. All right, not hearing or seeing any here in person. Thank you so much for your presentation and coming in and explaining your technology.
Thanks, guys.
We will, not Siri, we will be going to break. And as we know, I cannot tell time, so let me look. We will be coming back at 10:35 Eastern to start with the next presentation. Turn it up. Mute.
Okay.
So if I said something.
Yeah.
Yeah, Valentino, we can see you.
Awesome. Can you hear me as well?
Yep, perfect.
Good morning.
About 2 more minutes and we'll start.
Sounds great. Thank you.
I have to go off mute here. All right. Thank you, everybody, for joining. We're going to go ahead and start back up in our next round of presentations. If you are named Scott Furman and you have a number at the end of your name, you're not the real Scott. Please change it or let me know and I can change it for you. Let's give up to Bioforce Tech, Valentino, if you want to go ahead and take it away.
Thank you. Thank you so much. Hello, everybody. Good morning. This is Valentino Villa, the co-founder and the chief operating officer at Bioforce Corporation. Thank you so much for the opportunity of being here today and to presenting our sustainable solution for biosolids management. I will try to, what happened here? All right. I will try to manage it in 20 minutes and staying within the time, of course. The presentation is going to be divided in, let's say, 3 sections. And I normally begin with introducing the company, of course, and our mission and value proposition. BioForstar Corporation is being established in 2012 in South San Francisco, in the heart of the Silicon Valley in the Bay Area, with a mission of protecting nature and human health by providing technologies that deliver a zero waste future. So our goal is very much to being able to transform organic waste and biosolids specifically into sustainable products. If we look at today's situation, and this is also part of the reason why we're all here to present amazing solutions and systems, is that currently about 90% of biosolids and residuals in the US are disposed of in landfill or utilized as land application. We all know the situation, especially with the state of Maine, but other states and counties are following pretty much the same trend. So we're seeing, of course, landfill that has never been a great solution for organic waste and biosolids specific, although it, of course, it has its value. But we're seeing a lot of pushbacks from regulations and agencies as far as utilizing these biosolids between landfill and land application, right? So this is really why the reason we are here and why we keep pushing very hard to embrace more sustainable solutions for the betterment of our planet and our communities. So at BioForstar Corporation, we do see waste, of course, organic waste, as a real opportunity. There are so many benefits that we can bring to the table and to the communities that we serve that can be summarized in 5 micro points, right? So again, we focus around biosolid sustainable management systems. What we want to achieve are the following. The first is to being able to generate renewable energy from those biosolids, and there's quite a bit of energy content in those. Just needing a sustainable and efficient system to be able to extract that energy in the cleanest way as possible. Removing contaminants is another of our very high points and value propositions here, to being able to remove CECs, PFAS, PFOA, microplastics, and so on from the biosolid stream that we process all across the country. Sequestering carbon, so still benefiting from utilizing those biosolids in a cleaner way, but still benefiting from sinking that carbon and having nothing to waste as far as CO2 equivalent emissions. Creating renewable products, which goes very much along together with the transforming waste into a resource and being able to utilize the resource to make beneficial and sustainable products. Last but not least, of course, diverting organics from landfill disposal is the method that will increase the most our carbon sink and prevention. So, of course, that is last but not least in our mission and the vision for the future. The BioForstar system, as far as offering and value proposition, is a 2-step process. I'm not going to be talking too much about the first step of biological biodrying, simply because it's not too well applicable for this situation. It is a great and non-conventional drying system and technique that utilizes biology, mainly to being able to dry biosolids very efficiently and very reliably, but is also very effective on the small to medium scale. So again, I'm not going to be focusing too much, but BioForstar also has a proprietary solution that is called the BioDryer, to being able, again, to removing water from wet biosolids in order to then be transformed into a resource, into a product through the second machine that is an advanced pyrolysis system. So our combined system between biodrying and pyrolysis is meant to be installed directly inside the wastewater treatment plant, ideally as close as possible to the dewatering step, so where biosolids are produced. The system, so both machines can work and accept stabilized or unstabilized solids, so digested or undigested dewater sewage sludge. The requirements for biodrying are going to be a minimum of 17% dry solids, but of course we can plug in the pyrolysis step and solution to a dried product that has been dried through another drying system and technique, so long as we can meet some of the criteria for pyrolysis to be suitable for processing conditions. So biodrying, again, the goal is to being able to remove the water as efficiently and as reliably that we can, and then the pyrolysis step will be able to take on those dried biosolids to, again, extract value, stop producing waste, and transforming the organic waste, such as biosolids in our case, into high quality our carbon biochar. We offer modular and scalable solutions, and this is true for both systems. We have a great design that allows us to deliver fully built, fully assembled, and fully wired systems. So we can have customers that we serve that have a single machine as well as multiple machines in line. But again, everything we do and deliver is going to be pre-assembled, pre-built, and pre-tested at the factory and deliver as a fully built solution. So we also have customers who have begun with a partial diversion of their biosolids with a smaller installation to begin with. And of course, working together on optimizing design, configuration, and future growth, we have capacity to expand processing capacity in the future simply by adding units without changing anything that has been done prior. So very easy for us also to scale for future conditions, future growth without going full in immediately, but planning accordingly for the next 20, 30 years, and also offsetting some of the capital requirements for the communities we serve for multiple years instead of having a single year of massive expenditures for them. Again, the goal of the combined system here is to stop producing waste, but to start producing resources and products. Of course, removing CECs such as PFAS, PFOA, microplastics, it is something that we care about very much. And of course, being able to deliver a system as far as the combination of drying and pyrolysis that can be energy neutral from a thermal standpoint is another of our value proposition here, and something that it is possible with a combination of our both and combined machines. So biodrying, just quickly here, is a biological batch drying system that relies on mesophilic and thermophilic bacteria that are already present in the biosolid stream that the system receives and processes, in order to be very efficient and saving up to 70% of the energy compared to any other dryer that is available on the marketplace. It operates at 160 Fahrenheit as far as the maximum temperature, so about 65 degrees Celsius. So that brings a lot of reliability and ease and safe operations compared to other dryers that may be operating at 300, 400 degrees. Of course, with some concerns as far as reliability and the safety. Again, can work with digester and digested sludge. It is best for implementation between 1,000 and 10,000 wet tons per year, and is of course fully automated with 24/7 operations and 95% up running time. The output from biodrying is going to be Class A or EQ compliant. We follow EPA 503 to achieve that status. Of course, some of the parameters will need to be in line and online within the biosolids that is fed to the system to result in a Class A or EQ compliance product. Some pictures just to show scale, implementation, and how we design projects. This is a picture in a system with 3 units. This is another one with 7 units, 4 units, and 2 units. So just again to show modularity, scalability, and just as a reference, a single dryer has the capacity of about 1,000 wet tons per year. So if you see 7 biodryers being installed, there will be a facility that is able to process up to 7,000 wet tons a year, and so on. So again, this is just for references and to show you how we design and install these systems. This is a snapshot of the manufacturing facility. Everything we manufacture is currently done in the northern side of Italy, and we have about 40,000 square feet of space available for which we can produce up to 30 machines per year at the moment. Switching side to what is most, of course, of interest for today's presentation and discussion is our pyrolysis system, which is the second machine. It's the system and the solution that is able to, again, giving value to waste, producing high quality or carbon biochar, producing renewable energy in form of hot water that, of course, our dryer can benefit from to reduce the needs of any energy from the outside, removing CECs, again, such as PFAS, PFOA, microplastics, and of course, we still follow the modularity and scalability aspect of this solution and system as well. I would like to state that our system has been designed for the ones of you who are familiar with pyrolysis. I'm sure you've heard some of the presentations before. We designed our system not to produce any tar, any oil, and avoiding any type of condensation of hydrocarbons onto the end product. So we can guarantee a very high quality of carbon product at all times, and of course that will be in line also with new regulations and carbon credits issuance, because of course we have met all of the highest conditions for quality and for reliability. Briefly talking about permitting, Biofossil Corporation, I believe, is the company that pioneered the pyrolysis movement across the United States of America. We had to face and deal with the first ever done installation on municipal biosolids in the US for pyrolysis processing. So of course it was a very challenging time for us, but we were successful. We received back in 2016 the exemption from the EPA as far as not being considered an incineration technology, not subject to any of the SSI requirements, but has been certified and deemed as a pyrolysis system. With that in hand, of course, not knowing, I have to be honest, I come from Italy, so I wasn't fully aware of how difficult that was going to be. But we chose San Francisco as the #1 installation for our company, and that was a very lengthy process for us for permitting reasons, because again, it was never been done before. So it took us about 3 years to get the full permit from what I consider the most stringent air district in North America and potentially in Europe as well, which is the Bay Air Quality Management District. So after 3 years of intense permitting application and processing with them, we received the full permit and never had a permit violation since then. We were able to develop many more installations throughout our journey in the United States and in Europe. Permitting applications now are much quicker, easier, and that is, of course, thanks to all of the data and information that we collected throughout all of our years of processing municipal biosolids at full scale. Some of the references and customers who are embracing our sustainable system and solution, we now count 8 biosolids facilities in the US with more than 30 machines being sold, installed, or yet to be installed. You can see some of the dots on the map. And another great market that we serve is, of course, Italy, where we have 8 biosolids installations with more than 20 machines being sold and utilized on that part of the world as well. So just to summarize it again, everything we do very much surrounds around the biosolids industry and world. That is truly our bread and olive oil, and that is truly what we focus on. Switching section to our carbon, which is again the product that we produce from our advanced treatment system. We call it our carbon because it is our waste. At the end of the day, biosolids is everybody's waste. It is our planet that we need to really take care of in a better way. So that is why we call it our carbon. It is a trademark, and we identify again the quality and the composition of the product that is produced from our advanced systems. The concept is extremely easy to think about it, although sometimes difficult to execute. But what we position ourselves is to diverting organic waste and biosolids from bad disposal practices, transforming them and applying our carbon where it's needed the most. We've done a very extensive research and journey as far as giving the most value on a sustainable and of course monetary aspect on our carbon product, and we started utilizing as a soil amendment. Of course, the most straightforward and immediate answer for our questions of what to do with the end product. That was back 5-6 years ago, but then about 3 years ago we expanded our research and application fields, and we started looking at our carbon as truly a new material. Nobody's really producing it at the moment other than Biofossil Corporation in the US. So we needed to create markets. We needed to get creative on uses and applications. So we developed amazing fields for applicability of this product. And now we can narrow those down to mainly 3 fields and industries that we serve. Soil amendment, of course, concrete and pigmentation are the 2 new avenues, let's call it that way, that are pushing a lot of the product in a beneficial and sustainable manner. So concrete, we position ourselves to replace some of the sand and aggregate material to being able to deliver a structural grade, sustainable and carbon negative concrete product. And pigmentation Our goal is to, of course, be as carbon mindful as possible. So we position ourselves to replace carbon black and utilizing our carbon as a black pigment for different and several applications that go from polymer to fashion to automotive, shoe wear, and so on. At Bio4Site Corporation, as part of our value proposition, when we identify partners that deal with biosolids, we also offer a guaranteed offtake agreement for beneficiary use for the entire production of our carbon at no cost to all of our utility partners. That is going to be available for the next 20 plus years. So waste is not a waste any longer. It becomes a resource that we will be very happy to manage on behalf of our customers, again, at no cost for the next 20 years. Last section I wanted to cover is our findings and results on PFAS and CECs. I have to be honest, I didn't fund the company in 2012 because I wanted to get rid of PFAS. I just didn't know. I have to be honest, I was ignorant to that aspect. But in 2018 is when we first started to hearing, there was a sort of a new problem facing the the fate of all of us that work very hard on biosolids and to find the best solution out there for the communities that we serve. So in 2019, we decided to entertain the first testing at full scale with our equipment. We identify 38 target PFAS and PFOA compounds, and of course, we run some independent testing on wet, dried biosolids and the resulting our carbon from the same processing train of the equipment. We utilized a certified lab here in California, and out of the 38 compounds, about 20 of those were identified in the wet and dried biosolids, but nothing was detected in the carbon product that the system produced. We were very excited, very happy to be seeing these results, but of course we knew that there was going to be so much more to be, discovered. Even today, there is still so much that is unknown, but we're working very hard on finding the right answers and solutions, of course, for all of the people that we serve. So in 2020, we had the opportunity to work with US EPA. They had assembled a great team, the PEAT task force that was very much focusing on PFAS solutions. So they were looking for solutions in able to destroy PFAS, and we were the only company that had an up and running system for municipal biosolids. Of course, we decided to work with US EPA and trying to find some of the answers that were missing. So the main two questions were, can we eliminate PFAS from biosolids? And if so, how and where are they destroyed? So the test was conducted in August 2020. 41 PFAS were analyzed compared to the 38 from the previous testing. The biodrying and the pyrolysis system were the equipment that had been tested. 6 1-hour tests, and we analyzed wet and dried biosolids, our carbon biochar, tap water, scrubber water from the pyrolysis system, and also stack testing utilizing a novel method. Since back in 2020, the EPA didn't have an official testing method approved. So we utilize FTIR and canisters for that scope. Results came back very positively, again, especially on the solids metrics. Again, the wet and the dried biosolids confirmed the findings of the 2019 testing. About 20 compounds were identified in the wet and in the dried matrix. But our carbon biochar came back again with non-detector levels all across the 41 analyzed compounds. So that was amazing for us to be also, confirming the same findings with the EPA study, and that was again very encouraging. Results on the tap water and on the scrubber water were very positive as well, in the sense that we have a scrubbing device for the pyrolysis system before going at the stack that takes care of some of the sulfur content of the biosolids, and of course it is quenched with city tap water. So results were in line in the sense that the city tap water had some PFAS and PFOA compounds detected in that stream, and the scrubber water, so discharge water, had the same levels and concentrations very much in line with whatever was found in the city tap water. Stack air emissions were the $1 million question, and now it's probably $10 million question, but they were very encouraging as well. Again, I need to say that the testing method utilized was novel, not formally approved, but what has come up from those data is some inconsistency in the results, in the sense that there were a weak observable CF4, C2F6, and some other compounds that may have been related to the dynamic spiking gas utilized for the test. Indeed, these results were not confirmed by the canister measurements that did not show any of the 17 analyzed fluorinated compounds above the detection limit of the instrument utilized. So again, that was very encouraging. I think to date, our company, BioProSec Corporation, is the one that fully embraced the problem, trying to find sustainable solutions for this big issue that is present all across the world pretty much. We are well aware that there is still a lot of work that needs to be done, but we position ourselves always to the front line to be as honest and transparent and to fully be invested to find out if this solution is truly effective, which we do really believe so. So a peer-reviewed article was released in 2020 in February with all the studies with the EPA that is, of course, public domain. So I'll be happy to share that for the full reading. Findings can be summarized here. So the BioProSec system, the pyrolysis step has shown great effectiveness to remove PFAS from the solid matrix, not leaving anything in our carbon product at the end. Small traces of PFAS were found in the scrubber water, but were comparable with the city tap water. And definitely more extensive source testing should be performed again, ideally utilizing the newest method from the US EPA. But so far, we're very comfortable and proud of the results that we obtain, knowing, of course, there's still a little bit to understand and to discover. We have assembled a great team of very high-end professionals that will be performing new testing, hopefully at the beginning of 2024. So we are looking forward to be filling all the gaps, missing information, and of course, to be presenting new and accurate data to the industry in the next few months. But again, to date, we do believe we have a great solution in hands that can be embraced all across the country and finally positioned ourselves and all the communities that we serve in a very sustainable manner. So that was the end. I hope I managed the time a little bit efficiently here, and I would like to open it up for Q&A if anybody has any questions.
Great. Thank you, Valentino. Yeah, if anyone in the audience, we have about 2 minutes for questions. Anyone here have questions? Is that turned on, Mac? Here, this is on.
Well, it's just interesting that you're not seeing the PFAS. Are you then speculating that you're removing the fluoride compounds in pyrolysis, or what's your belief about what's going on with the PFAS?
So I am not speculating that, in the sense that I was pretty clear that these data are still preliminary, in the sense that we did a lot of work, but still there are a lot of questions to be resolved and to be answered. So what I am presenting is the true fact that our system seems to be able to remove PFAS from the solids as far as nothing comes up in the biochar at the end. Nothing seems to be in the discharge water, but we know that we need to understand more the data and the effectiveness of this system. Personally, I do believe that our system is going to be effective at removing and destroying these compounds, but I do not have the certainty of it because, again, we're seeking for new testing in the near future, hopefully to be finally stating that once for all.
Time for one quick question.
I have a question. Would you consider turning our carbon into activated carbon? Has that been considered?
That's a great question. So the principle behind producing activated carbon and our carbon, it is very similar. We do not go through the physical or chemical activation of the biochar that we produce. So the surface area is about 1/4 compared to a regular activated carbon. You can theoretically achieve the same results for absorption and removal of whatever compounds you need to filter through the granular activated carbon, just increasing the amount of product, so our carbon versus activated granular carbon. So we have not done too many studies on it because we have a lot going on, as you have seen, but we have a lot of partners in the US and in Europe that are testing our carbon as a replacement for activated carbon filtration. So I do believe that is possible. We can also consider some further processing and activation to increase the surface area and the sort of a porosity and absorption properties of our carbon, but at the moment it is not what we are trying to do with our carbon. There are so many interesting and amazing fields for applicability that, again, we can offtake as much product that we can. There is not enough biosolids, honestly, in the world to be even fulfilling the demand of the concrete industry. But of course, the more research, the more findings as far as being able to reutilize our carbon in a beneficial and sustainable manner, the happier we will be. So I do think it's possible, but there might be something extra to be added to the processing train to get to the same results of a regular activated carbon. Otherwise, you need to use more quantity potentially to get to the same results for absorption.
Perfect. Thank you so much, Valentino, for presenting on Bioforce Tech.
Thank you.
Stop sharing, and there's information there. And we now have Michael from Earth Care, I believe, is next. If you want to go ahead and start projecting.
All right, good morning.
Good morning.
Okay. Now, can you see my screen?
Yes, we can. And you are sharing in slide mode.
Correct, okay. Good morning, everyone. I am Mike McGolden with Earth Care and Earth Care Solutions. And I'd like to take 20 minutes today to introduce you to who we are and what we can do. Well,
If you want to put it in presentation mode, that may help.
there we go. Okay.
Perfect.
Earth Care, we have been, our management team has been together for about 20 years. We have been developing projects during that time period with other technologies, and then in the last 11 or 12 years with our own patented technology. This photo that you're looking at is an installation in progress. We are putting a system in Bethel, Pennsylvania, with 2 gasifiers that will be processing biosolids and poultry manure. Our company has, over the years, we have been focused on a variety of feedstocks, predominantly non-wood related, whether that is municipal sludges, MSW, agricultural waste, all manners of organics, but typically the higher ash feedstocks that present an environmental issue with disposal. It's kind of amazing to me that every week I see an article or I hear someone say that gasification is an exciting technology for solving these problems, but it is not proven. It is still in the R&D state, or the facilities that are out there are at pilot scale, but nothing is commercially available. And nothing can be more wrong. We have 10 operational systems, all at a commercial scale. We're currently installing 2 more in Pennsylvania and have, a dozen others that are in some level of development. The oldest system we have has been processing dairy manure, and it's been in operation for 11 years. There have been upgrades to our technology over the years, but it is still basically the same gasifier, which is capable of processing about 40 dry tons per day. We've got one facility it's been operating for 2 years, 24/7, that has processed over 500 tons a day of poultry manure and has produced over 1,200 tons of biochar in a month. So, the concept that the technology is not commercially available is just not true. I don't know at what stage you have to get to before people start recognizing that, that there are proven technologies out there that can become commercially operational in a short period of time. We have processed some wood, but typically we have focused on other feedstocks. We have processed every type of animal manure that I know of: biosolids, MSW, bagasse from sugarcane, digestate, shea nut waste, spent mushroom substrate, distiller's grain, just a wide variety of feedstocks with the same equipment. There are operational differences when you go from feedstock to feedstock, but it is still the same basic equipment. We do not supply a technology. We supply a solution. When we develop projects, we put in the entire system, and including training operators and startup. The systems that we have in operation have all been sold systems. The system in Bethel is the first system that we will own and operate ourselves. But we have typically just sold equipment to customers. One of the pieces of, obviously, of any of these projects is, if the technology works, that's great, but they still have to be economically viable. And a big piece of what we have felt for 15 years that is necessary for the economics is to make a value-added product out of the byproduct. And so we have spent a lot of time and effort over the years developing and what we call our biochar, ecochar, into a variety of applications. So it's not just making the technology work. It is coming up with a beneficial use for the byproduct. And to that end, EarthCare have spread our wings and have started two other companies, EcoChar and EcoChar Environmental Solutions, to specifically focus on the char and the research and the marketing of that char. We are taking typically products that have an environmental impact, a negative environmental impact, and turning that material into a product with beneficial use. And the end products, there's the agricultural applications, there is remediation, there's filtration through stormwater and just pure water filtration, and carbon sequestration. It's been over the last few years, there's been just a worldwide change for how the world views carbon, and whether that's carbon credits or just decarbonizing our system and being able to produce a product that sequesters carbon has a lot of value that a few years ago was not perceived as such. All chars are not created equal. There's a lot of research that has been done concerning biochars, but it's typically been done with wood-based chars. The chars from manures and biosolids have some very unique characteristics. And it is driven by the minerals that are in the chars. And in a lot of cases, it is the phosphorus and the calcium that drives that. They provide an ionic particle charge that attracts heavy metals, that has a totally different application and totally different reaction when you use those chars. One of our companies, EcoChar Environmental Solutions, that has been the main driving factor for that company, is looking at how it absorbs heavy metals and how do we make designer chars to enhance that ability. Over the years, we have sold char for pure land application for row crop farmers. I mean, we have spread thousands of tons of char in cornfields and soybean fields for the ability to provide nutrients, to prevent leaching, prevent runoff of phosphorus and nitrogen, moisture retention. There's a lot of values that it provides for the soil. We have a PhD microbiologist that works with us that has taken these chars and added additional components and produced a formulated balanced fertilizer utilizing 40% char, and then the other 60% is bat guano and feather meal and meat and bone meal and a lot of the components you typically see in fertilizers. These are more gardening, more greenhouse related, but it provides another application for chars. We've used chars and sold chars into mostly poultry operations for animal bedding. The addition of char in with their bedding reduces the moisture content in the barns and reduces the ammonia release. We have proven data that shows we can reduce the ammonia release from a poultry barn for the life of a bird by more than 50%, which in today's market may not be that critical, but when they start regulating those emissions, it's going to become a very critical factor in the poultry industry. Odor control. We have several customers that are buying char just simply for the odor control that it brings. Water filtration. We're using in stormwater retention for nitrogen and phosphorus removal. There is a huge application in water filtration. Moisture retention. I mean, one of the main selling factors for any biochar is its ability to absorb moisture and hold it. And we've even done testing with the American Mushroom Institute, where we have replaced a percentage of the peat moss in mushroom substrate and used the char as a component of their substrate. I heard the question earlier about activated carbon. The activated carbon market is huge, and the product of choice so far is granulated activated carbon. Granulated activated carbon has a surface area anywhere between 800 and 1,000 or 1,200 meters squared per gram. We are in the 150 to 250 range. So we do not have the surface area that granulated activated carbon has. However, we have done testing where we have outperformed it, and by a wide margin, depending on what you're trying to do. Heavy metals, and because of the particle charge, the manure-based biochars have outperformed GAC in a lot of those applications, including PFAS contamination. And when you start looking at the cost of GAC versus the cost of biochar, and you look at the carbon footprint for the manufacturer of granulated activated carbon, there are a lot of benefits that biochar brings that granulated activated carbon does not. Again, we have a company that is devoted purely to that type of research and that type of marketing. We have sold, if you look at these photos, we've sold some, and they were geotextile socks filled with char that were used in a lead remediation application for stream restoration. There's just so many applications where the chars provide a benefit environmentally. We have installed 10 systems. We've got one in Indiana, we've got one in Ohio, Georgia, we're putting one in Pennsylvania. We've got 4 gasifiers in Saudi Arabia. We put in 2 projects in Russia, and this is before Mr. Putin decided that he wanted to take on the world. And then we've got one in the Netherlands. So we've got facility, and the predominant feedstock for these are some manures. I mean, it's hog manure, it's chicken manure. And we've got a facility running with 70% moisture egg layer manure, which is probably as close to what you see on the raw side with biosolids as you're going to see. And these photos are just different facilities that we have installed throughout the world. And the bottom part of this slide, prior to developing our own technology, I mean, we had a technology, or we had a system on the campus of Southern Illinois University that we tested fuels for 8 years. We put in a system in West Virginia many years ago on a poultry farm. We put another one in Minnesota. So we have spent a lot of years putting in systems, and quite frankly, learning what to do and what not to do. And in some cases, learning what not to do is more important than learning what to do. This is, and it's one of our operating screens that shows the gas fire. That shows you a cutaway version of what the gas fire looks like. It is, and you look at it at face value, it's a fairly simple looking machine. And, to us, that's one of the attributes. It is not overly complex. Having said that, there's a lot of features in there that are very critical to making it work. On the right side of the screen, there is a photo of one of our latest installations. That the right side of the screen and the bottom of the screen are both photos of the system in Saudi Arabia, which is 4 gas fires. And again, it's been running for 2 years now. And as we develop these projects, hand in hand, we are working to develop the markets for the associated chars that are produced, from those projects. This is kind of a rough depiction. This is roughly taken off of the project we put in Indiana, but it provides a very simplistic look at what one of these systems look like. And we've used it a lot to help explain to people how the process works. Typically, almost every project we have, we are taking the energy that we're producing in the gas fire and utilizing it to dry our feedstocks. We are normally dealing with feedstocks that are high moisture. So we are able to use the energy for evaporation of water through a drum dryer. And this system just basically shows feed going into raw material bins, which feed into a drum dryer. The material's dried, it goes into a cyclone separated from the air and returned back to the gas fire for processing and making char. Probably the only thing different from this depiction from a lot of our facilities is this shows a fan going to a stack, and depending on the feedstock, we will use a biofilter, the poultry manure, the biosolids. Some of those materials create an odor, not from the gas fire, but from the drying process. And so we utilize a biofilter to eliminate any odors. Currently, we're installing a system in Bethel, Pennsylvania, that will process a mixture of biosolids and poultry, whether that's chicken manure, spent hens, some type of agricultural residue. That facility will produce about 7,000 tons a year of biochar. These are simply photos that were at some stage of the construction process. We will be operating there sometime this fall, but we are still in the middle of that process. And here is just a quick layout photo showing what that system looks like, and including the building and the biofilter, and then that circle in the bottom left-hand corner there is an existing manure pit that we're utilizing that for the biobed, as it's already a built concrete structure. And that's just a little bit closer view of what the building looks like, with the gas fires feeding into a thermal oxidizer, into a blend chamber, and then into a drum dryer. And then we have, part of what we had to do with this process is this building is under negative pressure. So one of our requirements obviously is odor control. And so we have negative pressure to control all the odors, not just from the system, but from the raw material handling side of the project. Again, more photos just to show the things in progress of the facility there in Bethel. That's after the building is complete now, and most of the major equipment is already together inside. There's a drum dryer on the left. The photo in the middle is the majority of one of the gas fires is put together. And then the top right shows a gas fire and the oxidizer together. Again, more photos of that same facility. The upper right-hand photo is the motor control center. These systems are web-based remote access. So we have the ability to monitor them from remotely and also provide technical support without having to be on site. We did site work and were able to get on the property and start installation in May. We have completed the gas fires and dryers, and the building has been completed in about a 2-month period. The motor control center, one of the 2 motor control centers is there. We're running electrics now. And the biofilter will be on site in September, and then by the end of September will be operational. And then ramp up and commissioning is not a long process, so we'll be fully operational in October. It's been a little bit longer installation process than normal, simply due to some of the lead times with components with some of the vendors. We haven't had a lot of those issues in the past, and it seems that there's still some hangover from COVID, that there's still some components that are harder to get to. In the meantime, we've got a customer in Indiana, Riverview Farms, that's been absolutely wonderful. They have allowed us to bring people in and watch the system run. And we've had literally hundreds of people that have gone in and just to look at the equipment. And we've also been able to do a lot of testing with some materials prior to getting Bethel up and running. We started this project as Earth Care. As we started, we were introduced to an engineering firm that's their headquarters in Syracuse, Barton and Lejudas. As we move forward with this project, we both made the decision that there was some value in us working together. So we have formed Earth Care Solutions, and predominantly to work in the biosolid sector in the states where I think they have offices in 7 states. So, in the area where they have markets, where they have clients, there's a lot of opportunities with municipalities, with haulers in that area. The last few years, climate change, PFAS, algae blooms in waterways, a lot of the issues with managing waste has become more acute. I don't know that there's anything that's new. It has just become more recognized. And, the bad news is it's creating a lot of issues. I guess the good news is it's come to light that we can't ignore the problem any longer, and we need to address it. And we think Earth Care as that solution.
Great. Mike, we greatly appreciate the presentation you've given us. Unfortunately, we don't have time for questions in person, but I can have people type things in the chat. If you wouldn't mind just staying on at least for a few minutes to see if anything comes in the chat.
Okay.
And you can answer it that way. So thank you so much. We appreciate your time. If you can stop sharing, we can go ahead and get our next presenter. So we have Andrew from Char Technologies. I believe I'm pronouncing that correctly. You will definitely correct me if I'm wrong. If you want to go ahead, start sharing and begin your presentation.
Thanks, you pronounced that perfectly. Yeah, thanks to everyone for taking the time and allowing us to participate. I will share my screen and get started. Sorry, just bear with me for 1 second here. Everyone can see my screen.
Yep, we can now. Thank you.
There we go. Yeah, again, thanks everyone for taking the time. So Char, we'll try and keep this as brief as possible. We're based in Toronto in Canada. We're a publicly traded company on the Ventures Exchange for startups and mining exploration type companies. We have to share a legal statement because of our public status, but I won't read through it and bore everyone. Lawyers have to get paid. So Char is the umbrella and we're split into subsidiaries. We have a environmental consulting group, which helps on the permitting and compliance side. So any air modeling, water compliance work, Alltech can provide support as a third party for our projects. Char Tech Solutions is our technology division, so everything around pyrolysis is done through Char Tech, and Char Biocarbon is our operations division. Can operate our facilities across North America and does a lot of our testing and development work with regards to our outputs, both biocarbon and renewable energy or gas. The key piece here for Char Biocarbon is they can provide the offtake for the biochar that projects with our technology generates. So to provide that recurring revenue for a long term is always a bonus. I always like showing this slide. It just highlights the challenges of trucking sludge far and wide. And this is really what Char's mission is, to eliminate emissions, to decarbonize, and a lot of those emissions are associated with decomposition, transportation, trucking, and also landfilling. So Char's pyrolysis technology is high temperature pyrolysis. You could call it slow high temperature pyrolysis. It's about a 30-minute residence time. And we're operating in a temperature range now that we've pushed even higher. It used to be an average of 800 degrees. Now we're pushing to 850 and hoping to go to 950, even 1,000 degrees Celsius. Again, it's pyrolysis. There's no oxygen in our process. So it's thermochemical conversion. And we work with a series of different groupings of feedstocks. Today is all about biosolids, so I'll focus on that. So with biosolids, at high temperature without oxygen, we're converting biosolids into two outputs. Our emphasis is on making co-products, both syngas and biocarbon, also known as biochar. The syngas typically for biosolids, because it's usually higher in moisture, although we usually take it dried, and low in carbon content. The syngas quantity and application is limited to typically generating heat for our process and for the drying process. We also looked at making electricity because our syngas is clean, because we're operating at high temperature without oxygen. It can go directly into an engine, so that would be an option that we've looked at typically with biosolids. On the biocarbon side, if biosolids is the feedstock, we typically look at a traditional biochar fertilizer, soil amendment type application. Really like mixing with compost. It speeds up the compost time and adds a lot of value. And we've validated that we can eliminate PFAS at our high temperature. So there are other feedstocks. We work with digestating compost, and also wood is a great feedstock for pyrolysis. When we have more carbon, more fiber in the feedstock, we can generate even higher quality in different applications with both the gas and the carbon. On the gas side, our mandate is to make RNG from wood. And on the carbon side, we have a bio-coal product called Clean Fire that can be used for steel production. But again, that's dependent on a high fixed carbon or fibrous feedstock like wood. So these are some of our active projects that we've announced in the last year. Our flagship and where our pilot facility currently operates is in Thorold. That's our base project, where our pilot operates, and we're adding commercial scale kilns to process wood into both biocarbon or char that could be used as bio-coal, and make renewable natural gas. We used to be co-located with a digester in London, Ontario, where we processed multiple up to 20 types of digesting biosolids and different crops, and now the site is dedicated to processing wood because we're going to methanation there. We also have a project co-located with a biomass power plant called Greenleaf Power, and we recently announced a partnership with Synagro to deploy a demonstration system at several sites across the United States, with the goal of validating how we can integrate onto sites where there's Synagro operations and dryers already in place, and ultimately generate some biochar and demonstrate what we can do with that from a soil amendment standpoint. Validate our ability to eliminate PFAS directly at sites, and really do a lot of testing, specifically on the gas side, where we'll be deploying gas cleaning to understand the fate of PFAS, both in our gas and the wastewater fraction that's captured through our gas cleaning process. So Synagro is a well-established partner in the space, as everyone knows, and a great partner for us, and we're very excited to do more work with them and validate this directly on sites in the United States. So we often get compared to gasification because we're operating in a similar temperature range. The big difference is that there's no oxygen in our process. So that results in different qualities of gas. So again, our gas is high in calorific value. We don't need steam cycles if we want to generate electricity. Typically, gasification needs steam cycles to fuel a generator. And our biocarbon or char is going to be higher in fixed carbon because of the lack of oxygen. Biochar is being more widely accepted, which is great for the space. And obviously, I'm a bit biased. I think every technology has a great fit. Depends on the site, depends on the feedstock. If you just want to make a lot of gas, gasification is going to be better. So just want to clarify the difference from high temperature pyrolysis to gasification. So our pilot facility, which this is a picture where it was located in London, was used to do a lot of biosolids testing. Again, it's all about reducing carbon emissions, reducing mass by up to 90% can be a win in itself. And it's all about the outputs, the energy, or the syngas and the biocarbon and what we can do with it. So just to get a good feel for what our system looks like from a layout perspective, this is a system we designed for a digestate sludge, so a little bit higher solids content than what we typically see with biosolids. But we aren't dryer specialists. We integrate with other dryers. We believe there's a lot of great vendors out there, like Andrus, that are amazing at applying drying for biosolids. So that's typically something we can include, or typically something we would work with Synagro on for the drying side. And our goal is to get the material to at minimum 80% solids content or 20% moisture. We can actually run at any moisture content. We've gone as high as 70% moisture in some tests, but it's just not efficient from an energy standpoint. So if you get the material to 80% solids, that's ideal. 70% is really that break point where we would want to have a dryer. A lot of the projects we looked at, it's at 90% solids, the Class A product, which just means we're going to make more energy and more carbon or char. So the materials fed into our kiln, there's a rotary airlock, so that's what eliminates any oxygen from entering our process. It's a rotary tube kiln, so the material essentially is tumbled through a tube in this large box, and burners indirectly heat that tube, again, ensuring that it's oxygen free and in complete combustion, to high temperatures, typically 850 to 900 degrees Celsius. The burners typically need natural gas for startup, and then once we're running, we want to run on our own syngas. So there's two outputs that have to be managed. The biocarbon is cooled, can be dispensed into super sacks or trucks, whatever works best for the site. And the syngas or pyrolysis gas is untreated and needs to be cleaned. So we have developed a lot of process IP around our ability to crack the tar. Although we are operating at high temperature to reduce tars, there is still some present in the gas and condensables. So we eliminate those through a tar cracking stage, conditioning, scrubbing, traditional caustic and water wash scrubbers, which does consume a little bit of water and generates a small quantity of wastewater. That gas is then clean and we can use it for our process or send it to the dryer. There's also a lot of waste heat from our process that we can send to the dryer for other applications on site. And then finally, we have a thermal oxidizer in place for emissions control, running at an even higher temperature constantly to handle our whole gas load. There is space typically we design for wastewater treatment for the scrubbing, but often when we're integrating with wastewater treatment facilities, that can be sent right back, which is convenient. So typical footprint is about 4,000 to 6,000 square feet to have a comfortable space. Just to give you an idea of the process flow. So this is taking biosolids at 83% moisture. I'm just taking a specific case where a third party is providing it to us at 10% moisture, 90% solids, really great for our process. So we're operating our pyrolysis kiln. You generate about 30% in biocarbon, and the balance is a syngas that we clean. So you have a clean syngas that's generated, and there is some water again. So you can see the quantities of syngas after we've used it for our process that could be sent to the dryer based on this specific case and the waste heat. It's not to say that it's going to cover all the energy needs for the dryer, but it is all about closing the loop and generating as much energy for the processes on site. So we've done a lot of tests around PFAS. We did lab scale tests in 2021 with a bunch of biosolids feedstocks from the US and Canada, operating at lower temperatures, so 500 degrees and 700 degrees Celsius. We saw some PFAS come through at 500 degrees Celsius, which was expected. You're really concentrating mass, but not hitting a high enough temperature to eliminate all of the PFAS, these 28 contaminants. At 700 degrees Celsius, we did see complete elimination in the biocarbon or char output. So this led us to doing bigger pilot scale tests at our facility when it was in London at Stormfisher's site. And we analyzed both the char and the syngas. We operated the test at 840 degrees Celsius. We saw no PFAS in the char, but we did see small quantities of PFAS in the syngas. And to clarify, our pilot system does not do any gas cleaning. And this was only immediately after our kiln. So the deployment with Synagro, we're going to be doing gas cleaning or scrubbing. We'll analyze PFAS in the gas at every kind of stage within that process. And then also after our thermal oxidizers to do some stack testing. And we're very excited for those results. Our plan is to operate at, again, even higher temperature up to 850 to 900 degrees Celsius, where we're quite confident we won't see any PFAS in the gas. So I always like to show a mass balance. I think it tells a really good story. We typically focus on our biggest kilns. Our demo or pilot system, whatever you like to call it, is on the small scale, but on the big scale, our biggest kiln can process about 25,000 tons of biosolids dried. And again, you'll get about 30% out, 30 to 40, depending on the feedstock, density, composition. And we'll also generate carbon credits because it's biosolids based biochar or carbon. You generate a little less carbon credits than you do biochar. Again, that's because the fixed carbon content is a bit lower. And then that key number as well as the net available syngas. So that's after what we've taken for our process. That would be available for drying to offset natural gas that's consumed on site to generate heat. So that's really the mass balance, preliminary mass balance for our process. And I always like to show financials. So assuming that, natural gas is about $5 an MMBTU, biocarbon or char, to be conservative, we expected about $75 per ton. And carbon credits are typically trading at $120 per cork. And a tip fee is assumed is at $30. So you can see with our biggest kiln, there's a sub 5-year payback, including all the infrastructure that you need. So it gets more and more favorable as you go to our largest kiln, and that's really our sweet spot. We're more of an industrial scale kiln with regards to our largest. In terms of the biochar and carbon credit market, this is really an exciting space that we're seeing a lot of growth, and is changing the opportunities for pyrolysis deployments globally. Biochar has a lot of great benefits in terms of water retention, soil structure improvements, no odor. But the big thing is, again, the carbon that you sequester within that structure for thousands of years can be then recognized as credits and sold or retained by the project or the owner of the site. Again, we're seeing biosolids based char at $50 to $100 per ton. Anyone that's saying that they can get, thousands of dollars for char is, I think, not being realistic. Again, biosolids based biochar is lower on the fixed carbon side. So the carbon credit market is a voluntary market that's really exploded. Puro.earth is the leading platform. There's others, Carbon Future. There's certification platforms like Vera, that's US based, and Puro is now allowing you to pre-sell the corks that these projects generate to finance projects. So everyone recognizes that the carbon dioxide removal credits or corks are traceable. Unlike buying a plot of forest, you can truly trace where the biocarbon is made from and where it's going. So looking at the value, it's varied over time. We saw a big jump at the beginning of the year, and now it's at about just under $120 per cork. And it is a European-based company, Puro.earth, but if you look at their platform, American companies like Microsoft and Shopify are buying up all the credits, and there are also American companies generating biochar credits through projects across the US. So really exciting developments in this space. So again, our mandate is to eliminate PFAS, make some biocarbon that can be used as a soil amendment product, generate some carbon credits for additional value. But because we're operating at a higher temperature, we'll see a slightly higher carbon content. So we should generate a few more corks than a lower temperature process. And we'll generate high quality and excess gas if we're getting biosolids at 20% moisture or less. So that's where we really specialize. There's a lot of benefits in terms of greenhouse gas reduction, job creation. There's no odor. It's a quiet operation system. We like to be compact and scalable. So if we want to go bigger, we add more kilns. And we did get NECA issued by the Ontario Ministry here in Canada, which is probably not on par with California in terms of the rigor, but we always like to say is a close second. That was a quite intensive process. We've also engaged the EPA to go through similar sewage sludge incineration distinction to prove that we're not doing any burning. It's all about education, just showing that there's no oxygen in our process, I think was the first step. So Yeah, we're very excited at the opportunity to help eliminate the concept of waste, make some excess energy, and make a higher value biocarbon product that can sequester carbon. Sorry, I kind of ran through that really quickly, but I wanted to keep it short. I know everyone here is sitting through a lot of these. Appreciate everyone's time and happy to answer questions.
Great, thank you so much. We do have about 5 minutes left. If there are any questions, are there any here in the audience or come off mute? Okay, hold on, we have one here in the audience.
The history of pyrolysis, especially with wood waste and coal, has a long history of a lot of real negative carbon rings, benzenes and toluenes and, nasty stuff. You obviously have a lot of wood waste experience. What are you seeing in those, and how do you eliminate those nasty organics being formed?
Yeah, I mean, the big thing for us is that we're operating at a higher temperature. It's a great question. We've seen a lot of companies struggle, and traditional pyrolysis has operated at, I talk in Celsius, you can double it for Fahrenheit. It's usually about 500 or 600 Celsius. So we found that operating at 200 to 300 degrees higher temperature eliminates that. The other differentiator for us is with our gas cleaning process, we can eliminate some of those contaminants that do get through, even though it's at high temperature. And we have no interest in the oil fraction. It's really all about concentrating that in wastewater, and then you will see some of those compounds in the wastewater fraction, and it's a small fraction that we would need to deal with, dispose of in a safe way. But we've seen with wood, is a little less challenging than biosolids in terms of the gas contamination and the biochar. We're working with construction demolition wood, which has a lot of contaminants, but haven't had any issues with regards to the quality of the carbon and the quality of the syngas. But it's a good point. There's been a lot of challenges with pyrolysis, especially at that lower temperature range.
Okay, thank you. Are there any other questions? Great, thank you so much for presenting. We appreciate the time. Oh, was there a question? No, okay.
Sorry about that.
Oh, no worries. All right, so we are now at our lunch break. So we'll be returning at 1:15 Eastern time with our last presentations of the afternoon. Thank you so much, everybody.